Reality is a word humans use with confidence, yet rarely define with precision. We speak of reality as if it is solid, fixed, and complete, but in truth, it is a narrow window shaped by biology, physics, and limitation. To understand what might exist beyond the edge of reality, we must first understand what we mean by reality itself and why we instinctively believe it has boundaries. At its most basic level, reality is everything that exists independent of belief. It is the sum total of space, time, matter, energy, and the laws that govern them. Yet no human has ever experienced reality in its entirety. What we perceive is filtered through senses, evolved for survival, not for truth. Our eyes see only a thin slice of the electromagnetic spectrum. Our ears capture a narrow range of vibrations. Even our sense of time flows in one direction, locking us into a specific perspective from the very beginning. Human reality has been incomplete. Early humans believed reality ended at the horizon. Beyond the edge of the land was an ocean. Beyond the ocean, a void, monsters, or nothing at all. This pattern repeats throughout history. Every era places an edge where understanding fails. When the Earth was believed flat, the edge was literal. When astronomy advanced, the edge moved to the stars. When galaxies were discovered, the edge moved again. Reality never expanded, only our map of it did. This reveals an important truth. What we call the edge of reality is not necessarily an edge in existence, but an edge in knowledge. It is the point where observation breaks down, where measurement fails, and where prediction becomes speculation. Humans are uncomfortable with such edges. We instinctively want reality to be complete, enclosed, and explainable. A boundary gives comfort. Infinity does not. Modern science defines reality through measurable quantities. Space has dimensions. Time has duration. Particles have mass and charge. Forces obey equations. But even within this framework, cracks appear. Quantum physics shows that particles do not behave like solid objects until observed. Relativity shows that space and time are flexible, shaped by mass and motion. Reality is not the rigid structure it once seemed. It is dynamic, contextual, and deeply strange. This strangeness raises a fundamental question. If reality behaves differently at different scales, then what exactly are its limits? Does reality end where our equations stop working? Or does it continue in forms that are inaccessible to us? The idea of an edge emerges precisely because our tools have limits. Telescopes can only see so far. Experiments can only reach certain energies. Mathematics can only describe what it can formalize. Beyond that lies uncertainty, not necessarily nothing. The observable universe provides a powerful example. There is a maximum distance from which light has had time to reach us since the beginning of cosmic expansion. Beyond that distance, galaxies exist, but they are invisible to us, not because they are unreal, but because information from them cannot arrive. For an observer on Earth, reality appears to end at this horizon, but the universe does not end there. The edge is observational, not physical. This distinction matters. An edge of perception is not an edge of existence. Yet humans often confuse the two. Throughout history, whatever lay beyond observation was labeled unreal, mythical, or impossible. Atoms were once invisible and therefore hypothetical. Galaxies beyond the Milky Way were once unthinkable. Black holes were dismissed as mathematical absurdities. In each case, reality extended beyond belief long before evidence arrived. So why do humans persist in imagining an ultimate edge? Part of the reason is cognitive. The human brain evolved to operate within finite environments. We understand beginnings and endings. We understand borders and containers. Infinity overwhelms intuition. A reality without edges feels unstable, meaningless, or terrifying. Placing a boundary allows the mind to rest. Another reason is philosophical. If reality has an edge, then it can be defined completely. It can be measured, catalogued, and mastered. Without an edge, reality becomes open-ended, forever incomplete. This challenges not only science, but identity. If reality is boundless, then human understanding is permanently limited. Not temporally, but fundamentally. Religious and mythological traditions often addressed this discomfort by placing something beyond the edge, heavens beyond the sky, underworlds beneath the earth, divine realms outside physical space. These were not random inventions. They were cognitive solutions to the problem of excess reality. When the known world felt too small to explain existence, something greater was placed beyond it. Science did not eliminate this impulse. It refined it. Instead of gods and spirits, we now speak of dimensions, multiverses, and abstract mathematical structures. The language changed, but the motivation remained. We sense that what we experience is not all there is. Reality feels too deep, too consistent, too structured to end where our instruments stop. Even the word reality implies contrast. If something is real, something else is not. Illusion, dream, hallucination, simulation. Yet these distinctions blur under scrutiny. Dreams occur within the brain, which is part of physical reality. Simulations run on hardware composed of atoms and energy. Hallucinations follow neurological laws. The boundary between real and unreal becomes less clear. Perhaps reality is not a single layer, but a stack of interacting layers, some accessible, others hidden. This layered view changes the meaning of an edge. Instead of a wall, the edge becomes a transition. Beyond familiar reality may lie forms governed by different rules. Not supernatural, but natural in ways we do not yet understand. Just as microbes existed before microscopes, entire structures of reality may exist beyond current detection. Physics already hints at this. Forces that seem separate may unify at higher energies. Dimensions beyond the visible may influence gravity. Space-time itself may be emergent rather than fundamental. If this is true, then what we call reality is not the foundation of existence, but a surface phenomenon. The edge of reality would then be like the surface of an ocean, beneath which deeper structures operate unseen. There is also the question of whether reality is observer-dependent. Our measurements shape outcomes. Our reference frames affect time and space. If reality depends partly on observation, then different observers may inhabit different realities, overlapping but not identical. In such a universe, edges would not be universal. Each observer would carry their own horizon. This possibility is unsettling. It suggests that reality is not a single shared stage, but a network of perspectives constrained by information flow. What exists beyond one observer's reality may exist fully within another's. The edge becomes relative, not absolute. Yet, even if edges are relative, the question remains, is there an ultimate boundary, a final limit beyond which nothing exists? Some theories suggest reality may be infinite, without boundary in space or time. Others suggest a closed structure, finite but unbounded, like the surface of a sphere. In such a case, there is no edge to reach. Travel far enough in one direction and you return to where you started. Both possibilities challenge intuition. An infinite reality denies closure. A finite but edgeless reality denies direction. In neither case does the familiar idea of an edge survive. The very question may be flawed. Asking what exists beyond the edge of reality may be like asking what lies north of the North Pole. The concept breaks down, and yet humans continue to ask, because even if the question is flawed, the intuition behind it is not. We sense that what we experience is incomplete, that there are layers, depths, and scales beyond daily awareness. This intuition has driven exploration, science, and philosophy for thousands of years. It has been wrong in detail, but right in direction. The edge of reality, then, may not be a place. It may be a process. The continual expansion of understanding into regions once thought unreachable. Each time we cross an old edge, a new one appears further out. Not because reality ends there, but because knowledge always lags behind existence. In this sense, the edge of reality is permanent, not because reality is limited, but because understanding is. There will always be questions that cannot yet be answered, phenomena that cannot yet be measured, structures that cannot yet be imagined. The universe does not hide these out of malice. It simply operates on scales that dwarf human capability. This leads to a humbling conclusion. Reality is not built for us. It does not conform to human intuition or preference. It exists as it is, vast, layered, and indifferent. The idea of an edge reflects our position within it, not its structure. We stand inside a small illuminated circle, surrounded by darkness, mistaking the boundary of light for the boundary of existence. As this documentary unfolds, we will move step by step toward that boundary, not to cross it, but to understand what it represents. Each outline will push further into physics, cosmology, philosophy, and speculation, not to claim certainty, but to map possibility. Because beyond the edge of reality, whether literal or metaphorical, lies the deepest question humans can ask. Not what exists out there, but how much of existence we are capable of understanding. The observable universe is not the entire universe. It is only the portion of existence that has revealed itself to us through light, radiation, and measurable signals. This distinction is critical because when people speak about the edge of the universe or the edge of reality, they are almost always referring to the boundary of observation, not a physical wall or an ending of space itself. To understand this boundary, we must begin with light. Light is the fastest messenger in the universe. Nothing carrying information can travel faster than it. Every star we see, every galaxy we photograph, every cosmic event we detect reaches us only because light or other radiation has had time to arrive. If light from an object has not reached Earth yet, that object is effectively invisible. It exists, but it does not exist to us. The universe is about 13.8 billion years old. This number immediately imposes a limit. Since light travels at a finite speed, we cannot see anything farther than the distance light has been able to travel since the beginning of cosmic expansion. This creates a sphere around us, centered on our position, defining the observable universe. Its radius is roughly 46 billion light-years, larger than the universe's age might suggest due to the expansion of space itself. This boundary is often misunderstood. It is not a physical edge. There is no curtain, no barrier, no final wall of matter. Instead, it is a horizon, similar to the horizon on Earth. When you stand on a flat plane, the horizon appears to be a boundary, but it moves as you move. The land does not end there, your perception does. The cosmic horizon behaves the same way. If intelligent observers exist in distant galaxies, their observable universe would be centered on them, not on us. They would see regions of space we can never see, and we would see regions they can never see. Reality overlaps, but observation does not. This alone reshapes the idea of an edge of reality. It suggests that reality does not have a single, universal boundary. Instead, every observer carries their own edge, defined by time, distance, and the speed of information. Beyond that edge is not nothing. It is simply unobservable from that location. However, this limitation is not merely practical, it is fundamental. No improvement in technology can overcome it. Even a perfect telescope cannot see beyond the cosmic horizon because there is no signal to detect. Space itself is expanding, and in some regions it expands faster than light can traverse. Galaxies beyond a certain distance are not just far away, they are being carried away by the expansion of space so rapidly that their light will never reach us. This introduces a profound idea. Parts of the universe are not just currently invisible, they are permanently inaccessible. No future civilization, no matter how advanced, will ever observe them. They are causally disconnected from us forever. From a human perspective, this raises uncomfortable questions. If something can never be observed, measured, or interacted with, in what sense is it real to us? Physics answers clearly. It is real regardless of observation. Existence does not depend on accessibility. Reality is larger than what can be known. This forces a distinction between reality and empirical reality. Empirical reality is the subset of existence we can observe and test. Reality itself may be vastly larger. The observable universe is not the universe. It is a sample, limited by time and physics. Cosmic background radiation provides a striking example. When we look deep into space, we are also looking back in time. The most distant light we can see comes from a period about 380,000 years after the beginning of the universe, when atoms first formed and space became transparent. Beyond that point, the universe was opaque. Light could not travel freely. Information from earlier times is hidden behind a wall of plasma. This wall is not an edge of existence. It is an edge of visibility. The universe existed before that moment, but we cannot see it directly. Our understanding of earlier times relies on theory, inference, and indirect evidence. Again, reality extends beyond observation. This pattern repeats at every scale. There are energies too high to reach with current accelerators, distances too small to probe directly, times too brief to measure. Each limitation creates a boundary, and each boundary tempts us to mistake ignorance for absence. Human perception compounds this problem. Our senses evolved to navigate a world of meters, seconds, and moderate speeds. The universe operates across extremes of scale that the brain did not evolve to intuitively grasp. Billions of years feel abstract. Light years feel meaningless. Quantum uncertainty feels absurd. As a result, the true size and complexity of reality is psychologically flattened. Because of this, the observable universe often feels like the whole universe. It is already unimaginably vast. Billions of galaxies, each with billions of stars. What more could there possibly be? The mind resists adding more layers beyond this. Yet inflation theory suggests exactly that. The region we observe may be a tiny bubble within a much larger structure. During the earliest moments of cosmic history, space may have expanded at an enormous rate, creating regions far beyond our horizon. These regions would be real, structured, and governed by physical laws, yet completely unreachable. If this is correct, then the observable universe is not even representative. It is a local patch, shaped by chance initial conditions. Beyond it, the universe could look very similar, or radically different. The laws of physics themselves might vary. Constants could shift. Dimensions could behave differently. This possibility destabilizes the idea of a single, uniform reality. Instead, reality becomes contextual. What is true here may not be true everywhere. What we consider fundamental laws may be local rules, not universal ones. This does not mean science collapses. It means its domain is clarified. Science describes what can be observed and tested. It does not claim to exhaust existence. When science reaches the edge of observation, it does not say nothing exists beyond. It says we do not know. However, popular culture often fills this uncertainty with imagery: walls of stars, cosmic voids, empty blackness. These images mislead. Beyond the observable universe is not darkness or emptiness. It is more universe, structured, dynamic, and full of events, simply disconnected from us. The emotional impact of this idea is significant. Humans often imagine themselves at the center of reality, not necessarily spatially, but epistemologically. What we can know feels like what exists. The observable universe challenges this intuition. It places humanity inside a much larger whole, with access to only a fraction of it. This has philosophical consequences. Meaning, purpose, and significance must be reconsidered in a reality where most of existence is forever beyond reach. Yet, it also offers a strange comfort. Reality is not constrained by human limitation. It does not depend on our awareness. It continues regardless. The edge of the observable universe is therefore not an ending, but a reminder that reality is not tailored to human perspective, that knowledge is local, that understanding is provisional. As we push our instruments to greater precision, the observable universe expands in detail, not in size. We see finer structures, earlier times, subtler signals, but the horizon remains. It is built into the fabric of space-time. This means that the ultimate edge of observation is not a temporary challenge to be solved, it is a permanent feature of existence. Reality is fundamentally larger than what any observer can access. In this sense, the observable universe is both astonishing and humbling. It reveals an immense cosmos, yet simultaneously conceals an even greater one. The more we learn, the clearer it becomes that what we see is not all there is. The edge of reality, viewed through the lens of observation, is not a cliff but a veil. Beyond it lies continuation, not termination. The universe does not end where our vision fades. It simply continues without us. As we move forward in this documentary, we will go beyond this observational boundary conceptually, not by seeing farther, but by thinking deeper, exploring theories that attempt to describe what lies beyond the observable, and confronting the possibility that reality itself has no edge at all, only limits to knowing it. The speed of light is not just a number, it is a structural limit built into reality itself. Everything we know about distance, causality, and time is shaped by this single constraint. When we talk about the edge of reality, in scientific terms, we are often talking about the consequences of this limit, because it determines what can influence what can be known, and what must remain forever beyond reach. Light travels at roughly 300,000 kilometers per second. This speed is constant, regardless of the motion of the observer or the source. This fact, discovered through relativity, rewrote humanity's understanding of space and time. Before this, speed was relative and unlimited in principle. Afterward, reality gained a maximum rate of information transfer. Nothing carrying cause and effect can outrun light. This has immediate implications. When we look at distant objects in space, we are not seeing them as they are now, we are seeing them as they were when their light began its journey. A star 1,000 light-years away is seen 1,000 years in the past. A galaxy 10 billion light-years away is seen as it was 10 billion years ago. Observation becomes a form of time travel. As distances increase, this time delay grows so large that it creates a boundary. There comes a point where light from certain regions has not had enough time to reach us since the universe began expanding. Those regions lie beyond our observational reach. They are outside our causal past. This boundary is known as the cosmic horizon, but its deeper meaning is causal. It marks the limit of cause and effect. Events beyond this horizon cannot affect us, and we cannot affect them. No signal, no matter how advanced the technology, can cross this boundary if the expansion of space outpaces light itself. This leads to a subtle but profound shift in how we think about existence. Reality is no longer just about what exists somewhere, it is about what can be causally connected. Something may exist in a perfectly real, physical sense, yet have no possible interaction with us. From our perspective, it is unreachable in principle, not just in practice. This challenges everyday intuition. In daily life, distance is an obstacle, but not a fundamental barrier. You may be far from someone, but in principle, you can reach them given enough time and speed. The universe breaks this intuition. There are distances that no amount of time can overcome. Space itself expands, stretching the gap faster than light can close it. Because of this, the universe is not just large, it is partitioned. It is divided into regions that can never exchange information. Each region evolves independently after a certain point. This creates a patchwork reality, where what happens here has no bearing on what happens elsewhere beyond the horizon. This raises an unsettling idea. If parts of the universe are forever causally disconnected, then reality is fragmented in a fundamental way. There is no single, unified cosmic story that includes everything influencing everything else. Instead, there are many isolated narratives, each unfolding within its own causal bubble. From a human standpoint, our entire cosmic history is confined to one such bubble. Every star that influenced Earth, every galaxy that shaped our local group, every fluctuation that seeded our structure lies within this causal domain. Beyond it lies a vast unknown that will never touch us. Yet this unknown is not static. It evolves, changes, and obeys physical laws. It simply does so without any relationship to us. Existence does not require interaction to persist. It does not require observation. It does not require meaning. This forces us to separate two ideas that are often conflated: existence and relevance. Something can exist without being relevant to us. The speed of light enforces this separation. It draws a hard line between what can matter to us and what cannot. The concept of an edge of reality often arises from confusing relevance with existence. When something cannot influence us, it feels unreal. But physics does not support this intuition. The universe is under no obligation to be accessible. This limit also reshapes time itself. Because information travels at a finite speed, there is no universal present moment. Different observers have different slices of now. Events that are simultaneous for one observer are not simultaneous for another. Time becomes local, not global. This destroys the idea of a single cosmic now stretching across the universe. There is no moment in which the entire universe exists together in a shared present. Reality is temporally fragmented, just as it is spatially fragmented. When people ask what exists beyond the edge of reality, they often imagine a spatial boundary, but the deeper boundary is temporal and causal. It is the limit of shared history. Beyond that limit, events are not just far away, they are outside our timeline. This leads to a radical conclusion. The universe does not have a single history. It has many overlapping but incomplete histories, each centered on an observer's causal past. Reality is not a block experienced uniformly by all. It is a network of intersecting light cones. Our light cone defines our reality. It includes everything that could have influenced us and everything we could influence. Outside it lies a realm that exists but is disconnected. This is not science fiction. It is a direct consequence of relativity. Once this is understood, the idea of crossing the edge of reality becomes meaningless. There is no path that leads from inside a light cone to outside it. No amount of energy can change this. Even hypothetical faster-than-light travel would not merely move objects, it would shatter causality itself. This is why physicists treat the speed of light not as a technological limitation, but as a foundational rule. Breaking it would unravel the logical structure of cause and effect. Paradoxes would emerge. Timelines would collapse. So if faster-than-light travel is impossible, then the causal structure of reality is fixed, the horizon is permanent, the edge is built into space-time. This permanence has consequences for the ultimate fate of the universe. As expansion continues, more and more galaxies cross our horizon. Their light stretches, reddens, and eventually fades. They do not disappear physically, they disappear causally. They slip out of our reality. Far in the future, distant galaxies will no longer be observable at all. Future astronomers may see only a small island universe, unaware of the vast cosmos that once was visible. Reality will appear smaller, not because it has shrunk, but because causality has narrowed. This introduces a tragic element to cosmology. Knowledge is time-sensitive. There is a window during which certain truths are accessible. Miss that window, and those truths vanish forever behind the horizon. In this sense, the edge of reality is dynamic. It moves as the universe evolves. Regions that are part of our reality today will not be part of it tomorrow. Not because they cease to exist, but because they cease to matter to us causally. This reinforces a humbling lesson. Reality is not arranged for comprehension. Understanding depends on timing, location, and perspective. Our current era is unusually rich in information. We exist at a time when the universe is old enough to have structure, but young enough to still be observable. The speed of light is the silent architect of this situation. It defines not only what we can see, but what can ever be known. It enforces humility by ensuring that no observer can access the whole. So when we imagine what lies beyond the edge of reality, we must abandon images of walls and voids. Beyond the edge lies more reality, unfolding beyond any possible interaction with us. Not empty, not frozen, not meaningless, simply separate. This separation is not a flaw. It is a feature of a universe governed by consistent laws. Without a finite speed of information, reality would collapse into contradiction. With it, reality gains structure, order, and depth. The edge created by light speed is therefore not an enemy of knowledge. It is the reason knowledge is coherent at all. It shapes the universe into a place where causes precede effects, where histories make sense, and where reality, though incomplete to any observer, remains internally consistent. As we move forward, the next step is to confront an even deeper question. If reality is limited by causal horizons, does it have a shape at all? Is the universe finite, infinite, or something that defies both categories? Because once the speed of light defines how reality is partitioned, the next mystery is how big that reality truly is. The question of whether the universe is finite or infinite sits at the heart of human curiosity. It is one of the oldest questions ever asked, long before modern science existed, and yet it remains unresolved even today. When people ask what exists beyond the edge of reality, they are often unknowingly asking this very question: does reality end somewhere, or does it continue without limit? To ask whether the universe is finite is to ask whether there is a total amount of space, matter, and time. To ask whether it is infinite is to ask whether reality has no bounds at all. Both possibilities challenge intuition in different ways, and both have deep implications for how we understand existence. A finite universe suggests closure. It implies that reality is a complete object, something that could, at least in principle, be fully described. An infinite universe, by contrast, suggests that reality can never be exhausted, catalogued, or fully known. No matter how much we learn, there will always be more beyond. Historically, humans favored finiteness. Ancient cosmologies imagined domes, spheres, and layered heavens. Even when the universe expanded in scale, it often retained a boundary. Infinity was associated with chaos, divinity, or abstraction, not physical reality. Modern science disrupted this preference. When astronomers discovered that galaxies extend in all directions, the universe ceased to look like a contained structure. It began to resemble something open-ended. Yet openness alone does not guarantee infinity. Something can be vast and still finite. To understand this distinction, imagine the surface of a sphere. It has a finite area, but no edge. You can travel forever without encountering a boundary, yet the total surface is limited. Cosmologists consider similar possibilities for space itself. The universe may be finite in volume, but unbounded, meaning there is no edge to cross. If this is true, then the idea of an edge of reality becomes misleading. There would be no location where reality stops. Instead, space would curve back on itself in ways that are difficult to visualize. Reality would be self-contained but without borders. On the other hand, the universe could be infinite. Space could extend endlessly in all directions, containing infinitely many galaxies, stars, and regions. In such a universe, there is no total count of anything, no largest distance, no final structure. This idea is deeply unsettling. An infinite universe implies that every physically possible configuration occurs somewhere, given enough space. There may be regions identical to our own, copies of Earth, even copies of individual lives, not because of design, but because of sheer scale. Many resist this implication emotionally, but mathematics does not share human discomfort. The equations of cosmology allow infinite solutions as naturally as finite ones. The universe shows no obvious sign of an edge, no observable curvature that would demand finiteness. Current data is consistent with both possibilities. This uncertainty is not due to ignorance alone. It may be fundamentally undecidable. If the universe is much larger than the observable region, then its global structure may be forever hidden. We can measure local geometry, but global topology may lie beyond observation. This again blurs the idea of an edge. If we cannot determine whether reality is finite or infinite, then the edge may not be something that can ever be reached, even in theory. It becomes a question without an empirical answer. Yet the philosophical consequences remain. In a finite universe, reality has a total content. Even if unreachable, it is conceptually complete. In an infinite universe, reality is inherently incomplete from any perspective. No observer can ever claim to understand more than an infinitesimal fraction. Infinity also reshapes the meaning of rarity and significance. In a finite universe, events can be unique. In an infinite one, uniqueness becomes fragile. Given infinite trials, even the most unlikely events occur endlessly. This raises existential questions. If infinite versions of similar worlds exist, what does individuality mean? What does history mean? Does meaning dilute when repetition becomes inevitable? Some physicists argue that such questions are misplaced. Infinity may be a mathematical idealization, not a physical reality. Others argue the opposite, that rejecting infinity is an emotional response, not a scientific one. There is also a third possibility. The universe may be finite in some dimensions and infinite in others, or infinite in extent but finite in information, or structured in ways that do not fit classical categories at all. Reality may not conform to the binary choice humans prefer. Quantum gravity theories suggest space-time itself may be discrete at the smallest scales. If space and time are made of indivisible units, then infinity becomes more complicated. An infinite universe would require infinitely many such units. A finite one would require a maximum count. Yet, even discreteness does not eliminate infinity. An infinite grid is still infinite. The deeper issue is whether the laws of physics permit endless extension or enforce closure. Cosmic inflation complicates this further. Inflation suggests that space can grow faster than any signal can travel, potentially without limit. If inflation never completely stops everywhere, then new regions of space are constantly being created. Reality becomes not just infinite in size, but infinite in growth. In such a scenario, asking about the edge of reality becomes almost meaningless. Reality is not a static container. It is a process. Space itself is generated over time. There is no outer boundary, because expansion does not proceed into anything. It is not space expanding into emptiness. It is space expanding by redefining distances internally. This challenges common imagery. People imagine the universe expanding into a void. But expansion does not require an outside. It is the stretching of relationships within space. Asking what lies beyond expanding space assumes there is a background arena, but physics provides no evidence for such an arena. If space is all there is, then beyond space is not another place. It is an absence of spatial meaning. The question loses coherence. This does not mean the question is foolish. It means human language struggles to describe realities that violate everyday experience. Terms like beyond and edge come from spatial intuition. When applied to space-time itself, they may mislead. Yet humans persist because the intuition of an outside is powerful. We are used to containers. Rooms have walls, maps have borders, even ideas have limits. Infinity resists containment. This resistance produces a psychological tension. Part of us wants reality to be finite, orderly, and bounded. Another part senses that any boundary would require explanation. If reality ends, why there? What enforces the ending? What lies on the other side? A finite universe with an edge demands something beyond the edge, even if only as an abstract condition. An infinite universe avoids this problem by denying edges entirely, but at the cost of overwhelming scale. In this sense, infinity may be simpler. It removes the need for external explanation. Reality simply is, without boundary, no outside, no beyond. But simplicity does not guarantee truth. The universe does not care what feels elegant or comfortable. It follows rules we are still uncovering. Observationally, current measurements suggest space is very close to geometrically flat. This leans slightly toward infinite models, but does not prove them. A universe can be finite and still appear flat locally, just as the Earth appears flat to someone standing on a field. The deeper issue is that even if the universe is finite, its size may be so vast that it functions as infinite for all practical purposes. If the total extent is trillions of times larger than the observable region, then no experiment could ever distinguish it from true infinity. This leads to a strange conclusion. Whether the universe is finite or infinite may not matter operationally. Reality may behave as if it has no edge, regardless of its true structure. And yet, the human mind cannot let go of the question, because behind it lies something deeper than geometry. It lies a desire to know whether existence is complete or open-ended, whether reality is a finished story or an endless one. If reality is finite, then it is conceivable, at least abstractly, to imagine a total description. If reality is infinite, then incompleteness is permanent. No final theory can capture everything. There will always be more. This distinction affects how we think about knowledge itself. A finite reality invites the hope of final understanding. An infinite reality demands humility forever. As we stand now, science offers no final answer. Both possibilities remain open, and perhaps that is fitting. The question of finiteness or infinity may itself be part of the edge of reality, a place where human inquiry reaches its limit. What matters is not whether reality ends somewhere, but what its structure tells us about our place within it. A finite universe still dwarfs us. An infinite universe erases any claim to centrality entirely. Either way, the idea of an edge dissolves. Not because nothing lies beyond, but because beyond may not be a meaningful concept at all. In the next stage of this exploration, we move away from geometry and toward concept. Even if the universe has no physical edge, humans still speak of one. Why? What does the idea of an edge really mean in cosmology? And why does it persist, even when physics suggests it may not exist? The idea of an edge is deeply human. It comes from everyday experience, from walls, borders, horizons, and endings. When we apply this idea to the universe, we are not necessarily describing reality as it is, but translating the unknown into familiar language. In modern cosmology, The concept of an edge is less about a physical boundary and more about the limits of description, measurement, and meaning. Cosmologists rarely speak of an edge in a literal sense. Instead, they speak of horizons, limits, and breakdowns. These are not places you could travel to and touch. They are conditions under which current theories stop providing reliable answers. The edge of reality, in this context, is where explanation itself becomes uncertain. This shift is important. It reframes the question from where does the universe end to where does understanding end. The two are often confused, but they are not the same. Reality may continue smoothly while our models fail abruptly. One example is the singularity. Inside black holes and at the beginning of the universe, equations predict infinite densities and curvatures. These infinities are not believed to be physically real. They are signs that the theory has been pushed beyond its domain of validity. The singularity marks an edge of theory, not necessarily an edge of existence. This pattern appears repeatedly. Classical mechanics breaks down at atomic scales. General relativity breaks down at quantum scales. Quantum field theory struggles with gravity. Each time an edge appears, and each time deeper theories extend reality beyond it. This history teaches caution. Edges in physics often signal incomplete understanding rather than fundamental limits. What seems impossible under one framework becomes natural under another. However, not all edges are theoretical artifacts. Some limits may be intrinsic. The speed of light, for example, is not merely a feature of a theory. It is woven into the structure of space-time itself. Similarly, quantum uncertainty appears not as a technical flaw, but as a fundamental property of nature. Cosmology sits at the intersection of these two kinds of limits. Some boundaries may dissolve with better theories. Others may persist, no matter how advanced understanding becomes. The cosmic horizon is one such candidate. It is not expected to vanish with better instruments or deeper theories. It arises from the expansion of space and the finite speed of information. It is a structural feature, not a temporary obstacle. Yet even this horizon is not an edge in the everyday sense. It does not mark a place where something different happens. The laws of physics do not change at the horizon. Nothing dramatic occurs when a galaxy crosses it. It simply becomes unreachable. This makes the edge of reality invisible. There is no signpost marking where knowledge ends. The universe looks the same everywhere we can see. The edge is inferred, not observed. This invisibility contributes to misunderstanding. Popular imagination fills the gap with dramatic imagery. Walls of light, sudden emptiness, cosmic cliffs. In reality, there is no such spectacle. The universe does not announce its limits. Another source of confusion is language itself. Words like beyond, outside, and edge imply spatial relationships. But when applied to the universe as a whole, these words may have no clear meaning. If space includes all locations, then outside space is not a place. It is an absence of spatial definition. This creates a conceptual trap. The mind insists on imagining something beyond the universe because grammar allows it. But physics does not guarantee that such imagination corresponds to anything real. In modern cosmology, edges often appear as limits of predictability. There are regions of parameter space where small changes in initial conditions lead to vastly different outcomes. Chaotic systems amplify uncertainty. Beyond a certain point, prediction becomes meaningless even if the underlying laws are known. This kind of edge is epistemic rather than physical. Reality continues deterministically or probabilistically, but our ability to track it collapses. Weather systems offer a familiar example. The atmosphere obeys physical laws, yet long-term prediction is impossible. The early universe may have similar properties. Tiny quantum fluctuations magnified by inflation determine the large-scale structure we observe today. Beyond a certain point, the specific details are unknowable, not because reality is undefined, but because information has been erased or diluted. This introduces another kind of edge, the edge of recoverable history. Even if the universe is deterministic, its past may not be reconstructible beyond a certain time. Information is lost to horizons, entropy, and quantum effects. Black holes represent an extreme case. When matter falls in, information appears to disappear from the outside universe. Whether it is truly lost or encoded in subtle correlations remains an open question. Either way, the event horizon marks a boundary beyond which information cannot return. This makes black holes a local analogy for cosmic edges. They demonstrate how reality can continue internally while becoming inaccessible externally. Inside the horizon, physics proceeds. Outside, influence is cut off. These examples suggest that edges in cosmology are less about endings and more about separations. Separations between regions of influence, between scales of description, between what can be known and what cannot. This has philosophical implications. If reality includes regions forever beyond knowledge, then a complete description of existence may be impossible in principle, not just practically, but logically. Any theory we construct may describe only a portion of what exists. Some thinkers embrace this as a feature rather than a flaw. They argue that reality does not owe us completeness. Understanding may always be partial, and that partiality does not diminish truth. It simply defines its scope. Others resist this conclusion. They seek theories that eliminate edges, unifying all phenomena under a single framework. The dream of a final theory persists, a set of equations that describes everything that exists. Whether such a theory is possible remains unknown. Even if discovered, it may not eliminate edges of observation or computation. Knowing the laws does not grant access to all consequences of those laws. There is also the question of scale. Reality may be structured hierarchically, with emergent layers. Each layer has its own effective laws. Edges appear when moving between layers. What makes sense at one level becomes meaningless at another. This is seen in condensed matter physics, biology, and even economics. Macroscopic behavior emerges from microscopic rules, but cannot be easily reduced to them. The universe itself may operate similarly, with space-time and gravity emerging from deeper, non-spatial structures. If so, then the edge of reality may lie not in space, but beneath it, beneath space-time itself, beyond geometry, beyond duration, a domain where familiar concepts dissolve. This possibility is explored in quantum gravity research, where space-time is not fundamental. If space-time emerges from entanglement or information, then asking what lies beyond space-time is not like asking what lies beyond a wall. It is like asking what lies beneath a shadow. In this view, the edge of reality is a conceptual boundary, not a physical one. It marks where language, intuition, and mathematics begin to fail simultaneously. Yet even here, the word edge persists, because humans need markers. They need to know where understanding fades. edges provide orientation, even when they are abstract. The danger lies in reifying these edges, turning them into imagined places rather than acknowledging them as limits of description. When this happens, speculation can drift away from science and into fantasy. But careful speculation has value. It pushes theories to their limits, revealing where assumptions break. Asking about the edge of reality forces cosmology to confront its foundations. It asks what space is, what time is, what existence means when stripped of human perspective. It reveals that reality may not be a thing with boundaries, but a process with constraints. As this exploration continues, the next step is to move beyond abstract limits and examine specific proposals. If there is no simple edge, what do modern theories suggest exists beyond the observable universe? Not as metaphor, but as physical possibility. When cosmologists speak about what lies beyond the observable universe, they are not speculating wildly. They are extending well-tested theories to regions that cannot be directly observed. This distinction matters. What exists beyond our cosmic horizon is not fantasy. It is the natural continuation of known physics into domains cut off by distance and time. The simplest possibility is also the most conservative. Beyond the observable universe lies more universe that looks broadly like what we see here. More galaxies, more stars, more cosmic structure arranged according to the same physical laws. The same particles, the same forces, the same constants. From this perspective, the observable universe is not special. It is a typical region within a much larger whole. This idea follows directly from the cosmological principle, which states that on large scales, the universe is homogeneous and isotropic. In plain terms, it means the universe looks roughly the same everywhere when viewed at sufficiently large scales. There is no preferred center, no special direction, no unique location. If this principle holds beyond what we can see, then the universe does not suddenly change character at the horizon. There is no edge event, no transition. The horizon is simply the limit of our information, not a boundary in space. This alone answers part of the question. Beyond the edge of reality, as defined by observation, there is still reality operating normally. Galaxies form, stars burn, black holes grow. Cosmic expansion continues. Physics does not pause simply because we cannot watch. However, this conservative view may not be the whole story. The early universe underwent a period of rapid expansion known as inflation. Inflation was not just expansion, it was exponential expansion. Tiny regions of space were stretched to enormous scales in fractions of a second. One consequence of inflation is that regions of space that were once in causal contact were driven far apart. The observable universe today may represent only a small fraction of the region that existed before inflation ended. Beyond our horizon may lie regions that share a common origin with us, but evolved independently for most of cosmic history. Inflation also introduces the possibility that different regions of the universe ended inflation at different times. In some regions, inflation may have stopped earlier. In others, it may still be ongoing. This leads to a picture of the universe that is far more complex than a single expanding space. In this picture, our observable universe is like a bubble within a vast inflating background. Beyond our bubble, other bubbles may exist. Each bubble is a region where inflation has ended and conventional physics dominates. Between them lies inflating space that continues to expand at an extraordinary rate. This is not speculative fiction. It emerges naturally from many inflationary models, and it radically alters the meaning of beyond. Beyond the observable universe may not just be more of the same. It may be a fundamentally different environment. Inside our bubble, physical constants appear fixed. The speed of light, the strength of gravity, the masses of particles all have specific values, but inflationary theory allows for the possibility that these values could vary between different regions. If this is true, then beyond our observable universe, there may be regions where physics itself is different. Chemistry might not work the same way. Stars might not form. Stable matter might not exist. Reality would still exist, but in forms incompatible with life as we know it. This possibility forces a shift in perspective. The laws of physics we observe may not be universal. They may be local conditions, shaped by how and where inflation ended. What we call fundamental may be environmental. From our vantage point, this is deeply unsettling. It means that some of the deepest questions in physics may not have unique answers. Why does gravity have this strength? Why do particles have these masses? The answer may be not because it must be so, but because it happened to be so here. Beyond the observable universe, different answers may apply. Another possibility is that space beyond our horizon is structured differently on the largest scales. Even if local physics is the same, the global geometry of space may vary. There may be large-scale patterns, anisotropies, or topological features far beyond what we can measure. Space could loop back on itself. It could contain vast repeating structures. It could include regions connected in ways that do not fit simple three-dimensional intuition. From within our observable region, these features would be undetectable. We would see only a small patch that appears smooth and uniform. The larger structure would remain hidden. There is also the question of time. Beyond our horizon lies not only distant space, but distant past and future. Regions we cannot see now may become visible in principle, given infinite time, but cosmic expansion may prevent this. Some regions are not just far away, they are receding so fast that they will never become observable, even as the universe ages indefinitely. For all practical purposes, they are permanently beyond reality as experienced by us. Yet they continue to exist and evolve. Stars will live and die. Galaxies will collide. Black holes will evaporate. Entire cosmic histories will unfold without any connection to ours. This idea challenges a deeply ingrained assumption. Humans often assume that reality is defined by shared history. That to be real is to be part of a common story. Beyond the observable universe, this assumption fails. Reality fragments into countless independent stories. Another implication concerns probability. Many cosmological predictions rely on assuming typicality. We assume our region is not special. But if the universe beyond our horizon contains vastly more volume than the region we see, then most of reality lies elsewhere. What we observe may be statistically unrepresentative. Rare conditions may dominate locally while being insignificant globally. This complicates interpretation. Data from our observable universe may not reflect the broader cosmos. This issue becomes critical when discussing fine-tuning. The apparent precision of physical constants that allow complex structures has led some to argue for deeper explanations. Beyond the observable universe, there may be countless regions where constants differ and complexity never arises. In this view, our existence does not require special design. It requires only that some regions permit observers. we necessarily find ourselves in such a region, because no observers exist elsewhere to ask the question. This line of reasoning is controversial, but it arises directly from considering what exists beyond our observational edge. It shows how extending physics beyond observation reshapes not only cosmology, but philosophy. There is also a more radical possibility. Beyond the observable universe may lie regions not connected by space in any simple way. Some theories suggest that space-time itself may be a patchwork of domains connected through quantum processes. Entanglement, wormhole-like structures, or higher dimensional connections could link regions in ways that bypass ordinary distance. Such connections would not allow travel or communication in the usual sense, but they would imply that the universe is not a simple, continuous expanse. In this case, beyond the observable universe might not be far away. It might be adjacent in a higher dimensional sense, separated not by distance, but by structure. From our perspective, such regions would be completely hidden. No signal could reach us. No experiment could detect them directly. Yet their existence could influence fundamental physics indirectly through subtle effects on space-time or constants. This possibility blurs the boundary between cosmology and metaphysics, but it remains grounded in attempts to unify quantum mechanics and gravity. What all these scenarios share is a rejection of the idea that reality stops where observation stops. Beyond the observable universe lies continuation. Whether simple or complex, uniform or varied, accessible or not, reality does not terminate at our horizon. This has emotional consequences. Humans often imagine themselves at the center of existence, not spatially, but existentially. The idea that vast regions of reality exist entirely without reference to us undermines this intuition. Yet it also reinforces a profound idea. Existence is larger than meaning. The universe does not exist to be witnessed. It exists. This realization can feel alienating, but it can also be liberating. It frees reality from human projection. It allows the cosmos to be vast without justification. In this light, the observable universe is not a prison. It is a window onto a much larger structure that we infer but cannot see. What lies beyond that window may resemble what we know, or it may be radically different. Physics allows for both. Observation alone cannot decide. This uncertainty is not a weakness of science. It is a recognition of scope. Science describes what can be tested. When it extends beyond that domain, it does so cautiously, guided by theory rather than imagination. As we continue, the next step is to examine one of the most far-reaching consequences of these ideas. If reality extends beyond our horizon in varied forms, could there be multiple universes? Not metaphorically, but physically. And if so, what would that mean for the idea of reality itself? Inflation theory is one of the most powerful ideas in modern cosmology, not because it explains what we see today, but because it explains why the universe looks the way it does at all. It addresses problems that would otherwise seem mysterious, and in doing so, it pushes the concept of reality far beyond the observable universe. To understand inflation, we must return to the earliest moments of cosmic history. According to standard cosmology, the universe began in an extremely hot, dense state and has been expanding ever since. However, this simple picture leaves several puzzles unanswered. Why is the universe so large and uniform? Why does space appear nearly flat? Why do distant regions that have never been in contact look almost identical? Inflation was proposed as an answer. It suggests that shortly after the universe began, space underwent a brief but extraordinary period of expansion. During this phase, space itself expanded exponentially, doubling in size again and again in fractions of a second. This was not matter moving through space. It was space stretching everywhere at once. The effect of this expansion was dramatic. Regions that were once tiny and causally connected were blown up to enormous scales. Quantum fluctuations, originally microscopic, were stretched to cosmic sizes, becoming the seeds of galaxies and large-scale structure. Inflation explains why the universe appears smooth and uniform. It also explains why small irregularities exist. Without inflation, the universe would look radically different. But inflation also carries a deeper implication. If space can expand this rapidly once, there is no fundamental reason it could not do so again or continue doing so elsewhere. Many models of inflation predict that it does not end everywhere at the same time. In these models, inflation ends locally, creating regions like our observable universe where conventional physics takes over. But beyond these regions, inflation continues. Space keeps expanding at an enormous rate, spawning new regions endlessly. This scenario is known as eternal inflation. It implies that the universe is not a single expanding entity, but a vast, ever-growing structure containing countless regions where inflation has ended. Each of these regions is effectively its own universe. Our observable universe would be one such region, embedded in a much larger inflating background. Beyond our cosmic horizon lies not just more space, but a fundamentally different phase of space-time. In this picture, the observable universe is a bubble. Inside the bubble, expansion is relatively slow and structure forms. Outside the bubble, inflation continues, preventing structure from forming at all. The boundary between these regions is not a wall, but a transition between different physical regimes. This reframes the question of what lies beyond the edge of reality. Beyond our observable universe lies inflating space that will never become observable. It is expanding too fast for light from our region to ever reach it, or for light from it to ever reach us. These regions are not merely distant, they are causally disconnected in a permanent way. No event in our universe can influence them, and no event in them can influence us. Yet they are still part of physical reality. They obey laws, evolve in time, and contain energy. Their existence is inferred from the same theoretical framework that explains the structure of our universe. One of the most unsettling aspects of eternal inflation is its scale. If inflation never fully stops, then the total volume of inflating space grows without bound. New bubble universes form endlessly. Reality becomes not just vast, but effectively infinite in extent and diversity. This means that almost everything that can happen will happen somewhere, given enough time and space. Not just once, but endlessly. Reality becomes a generator of possibilities. Within this framework, our universe is not special in size or location. It is special only in that it permits complexity and observers. Countless other regions may exist where inflation ended differently, producing conditions hostile to structure. This leads to a profound shift in how cosmologists think about fundamental laws. What we observe as constants of nature may not be universal constants at all. They may be local outcomes of how inflation ended in our region. Different bubbles could have different values for particle masses, force strengths, or even the number of dimensions. Physics itself becomes environmental. This idea is deeply controversial, but it arises naturally from inflationary theory. Combined with modern particle physics, It does not require invoking metaphysics or speculation beyond established frameworks. It emerges when known theories are pushed to their logical conclusions. The idea that physical laws vary across regions challenges the traditional goal of physics. For centuries, physicists sought unique explanations, a single set of laws governing everything. Eternal inflation suggests that some features of reality may not have unique explanations. Instead of asking why the constants have their particular values, the answer may be that they vary across reality, and we observe the values compatible with our existence. This does not mean explanation ends, it shifts the focus. Physics explains the distribution of possibilities rather than selecting a single outcome. Beyond the observable universe, then, lies a landscape of realities, some similar to ours, many radically different, most likely barren and simple, unable to form stable matter or complex structures. From our perspective, these regions are forever hidden. No observation can confirm their existence directly. Their reality is inferred, not observed. This raises a philosophical challenge. Can something be considered real if it can never be observed? Even in principle, physics answers yes, as long as its existence follows from well-supported theories. After all, we accept the existence of the universe before recombination, even though we cannot see it directly. We accept the existence of black hole interiors, even though we cannot observe them. Reality is not limited to what can be seen. Inflationary regions beyond our horizon are similar. They are part of a theoretical structure that successfully explains observed phenomena. Rejecting them would require rejecting the framework that explains what we see. Yet this acceptance comes with discomfort. It implies that reality is vastly larger and more complex than anything accessible to us. It implies that our universe is one outcome among countless others. This undermines the intuitive idea that reality is singular and complete. Instead, reality becomes plural and generative. The edge of reality, in this view, is not an end. It is a boundary between phases of existence. Inside our bubble, time flows in a familiar way. Outside, inflation dominates, stretching space so rapidly that time itself behaves differently. Crossing this boundary is not possible. It is not a matter of travel or energy, it is a matter of cosmic history. Our region cooled and structured, others did not. This makes the edge asymmetrical. We can imagine what lies beyond by extrapolating theory, but we can never experience it. It is not just far away, it is inaccessible by definition. This raises questions about meaning and relevance. If most of reality is forever beyond us, does it matter? From a physical standpoint, yes. From a human standpoint, it challenges perspective. Human culture often equates importance with accessibility. What we can interact with feels real and significant. Inflationary cosmology breaks this association. It says existence does not require relevance. This realization can feel unsettling. It places humanity in a small, fragile region of a vast and indifferent reality. But it also provides context. Our universe is not isolated or arbitrary. It is part of a much larger structure governed by consistent principles. Even if we can never observe beyond our bubble, understanding that it exists reshapes our conception of reality. It expands the mental map of existence. In this sense, the edge of reality becomes a conceptual frontier, a place where physics meets inference, where observation gives way to extrapolation. Some critics argue that eternal inflation is unscientific, because it makes predictions that cannot be tested directly. Supporters respond that science has always dealt with unobservable entities as long as they arise from testable theories. The debate remains open, but the idea has already changed cosmology. It has reframed the universe not as a single object, but as a process, a continual unfolding of space and possibility. If inflation is correct, then beyond the observable universe lies an endlessly growing expanse of inflating space, punctuated by islands of structure like our own. Reality has no outer edge. It has phases, transitions, and domains. This means that the question, what exists beyond the edge of reality, has an unexpected answer. Not emptiness, not nothing, but more creation, more space, more potential universes. The edge, then, is not where reality ends. It is where our particular story begins to diverge from countless others. A boundary not of existence, but of narrative. As we move forward, the next step is to explore one of the most striking consequences of this picture. If inflation creates many regions, could some of them be fundamentally similar to ours? Could reality repeat itself? Could the universe, on the largest scales, be infinite and repetitive? The idea of a repeating universe emerges naturally once infinity enters the conversation. If space extends without limit and the laws of physics remain broadly consistent, then repetition is not just possible, it becomes unavoidable. Beyond the edge of our observable reality, the universe may not merely continue, it may repeat itself in ways that challenge the meaning of uniqueness, identity, and history. To understand this idea, we must separate emotional intuition from mathematical consequence. Humans experience repetition as rare and meaningful. Patterns repeat, but exact duplication feels extraordinary. In an infinite universe, this intuition fails. Infinity changes probability itself. If the universe is infinite in spatial extent and contains a finite number of possible configurations of matter within any given volume, then those configurations must repeat. This is not speculation. It is a direct implication of combinatorics. Given infinite trials and finite outcomes, repetition is guaranteed. Our observable universe contains an enormous amount of information, but it is not infinite. Particles have discrete states. Energy levels are quantized. Physical laws constrain how matter can arrange itself. Even if the number of possible configurations is unimaginably large, it remains finite. In an infinite universe, those configurations recur. Somewhere beyond our horizon, there would exist regions arranged identically to our own observable universe, not approximately exactly. The same galaxies, the same stars, the same planets, the same histories, unfolding in the same order. This conclusion feels absurd, even disturbing, but it follows logically. If certain assumptions hold, the discomfort comes from scale, not logic. Infinity is not intuitive. Some physicists argue that the universe is infinite and statistically homogeneous. If so, then repetitions are not optional. They are inevitable. The universe becomes a cosmic tiling of similar regions, each separated by vast distances beyond any possible interaction. These regions would not be copies in the usual sense. They would not be created by duplication. They would arise independently through the same physical processes. Chance, operating across infinite space, produces the same outcomes again and again. This idea reframes what exists beyond the edge of reality. Beyond our observational horizon may lie regions so similar that the difference between here and there becomes meaningless. Identity dissolves at cosmic scales. Yet this repetition does not imply synchronization. These regions are causally disconnected. They do not influence one another. They do not share a timeline. They simply exist in parallel, unfolding according to the same rules. This raises profound philosophical questions. If there are infinitely many regions identical to ours, then every possible outcome of events occurs somewhere. Every choice branches not metaphorically, but spatially. History becomes not a single path, but a distribution of outcomes. This should not be confused with many worlds' interpretations of quantum mechanics, which posit branching universes at every quantum event. The repeating universe idea requires no branching. It arises from spatial infinity alone. In this view, the universe does not split. It repeats. Some find this idea unsettling because it seems to undermine meaning. If everything that can happen does happen somewhere, what significance does any single event have? If identical versions of ourselves exist elsewhere, what does individuality mean? These concerns are understandable, but they arise from projecting human-scale values onto cosmic-scale structures. Meaning does not require uniqueness at the level of the entire universe. It requires coherence within a local narrative. Your experiences are meaningful because they are yours, embedded in a causal history that matters to you and those around you. The existence of distant duplicates does not alter that history. It does not interact with it. It does not diminish it. From a physical standpoint, identical regions elsewhere are no more relevant than fictional worlds. They exist, but they do not matter causally. This distinction between existence and relevance becomes critical. Infinite repetition does not collapse reality into redundancy. It expands it into multiplicity. However, not all cosmologists accept this conclusion. The repeating universe depends on several assumptions. One is that space is truly infinite. Another is that physical laws and constants are uniform across that infinity. A third is that the number of possible configurations within a finite region is finite. If any of these assumptions fail, repetition may not occur. For example, if physical laws vary across regions, then identical repetition becomes less likely. If the universe contains infinite information density, repetition may be avoided. If space is finite but unbounded, repetition may still occur, but in different forms. Inflation complicates this further. In eternal inflation scenarios, regions may not only differ in initial conditions, but in fundamental constants. This creates diversity rather than repetition. Reality becomes a landscape rather than a tiling. Yet, even in such landscapes, repetition can occur locally. Within regions where laws are similar, structures may recur. There is also a deeper issue. Repetition challenges the idea of randomness. If everything repeats infinitely, then randomness becomes a local phenomenon, not a global one. Outcomes are random within regions, but inevitable across infinity. This does not invalidate probability. It reframes it. Probability describes frequency within a finite domain, not uniqueness across an infinite one. From this perspective, probability is not about whether something happens, but how often it happens relative to other possibilities. This leads to a strange but consistent picture. In an infinite universe, everything physically allowed happens infinitely many times, but most of it remains forever disconnected. The edge of reality, then, is not a wall. It is a distance beyond which repetition becomes statistically inevitable. Yet this distance is incomprehensibly large. Estimates suggest that identical regions would be separated by distances vastly exceeding the observable universe, far beyond any horizon, far beyond any conceivable travel. These duplicates are not neighbors. They are mathematical consequences of infinity, not practical realities. There is also the question of time. Repetition in space does not imply repetition in time. The universe may not cycle through the same states globally. Entropy increases, histories diverge. Repetition occurs across space, not along a single timeline. This preserves the arrow of time locally, even if spatial duplication exists globally. Some have proposed even more radical ideas. If the universe is infinite in both space and time, then histories may repeat not just spatially, but temporally. After unimaginable durations, configurations could recur. This idea borders on speculation, but it highlights how infinity destabilizes intuition. Once finiteness is abandoned, repetition becomes difficult to avoid. However, cosmology remains cautious. Infinity is a strong claim. Current observations cannot confirm or deny it. Space may be finite, but extremely large. The universe may be infinite, but structured in ways that prevent exact repetition. The key point is not whether repetition occurs, but what its possibility reveals. It reveals that the universe beyond our observable reality may be governed by statistical inevitability rather than narrative uniqueness. This challenges human-centered views of existence. We prefer stories with beginnings, middles, and ends. Infinity offers distributions instead. Yet even within this vastness, local meaning persists. Causality, memory, and identity operate within regions. Repetition elsewhere does not interfere. In fact, the existence of repetition may be the price of consistency. A universe governed by simple, uniform laws extended across infinite space cannot avoid producing the same outcomes repeatedly. If this feels uncomfortable, it may reflect a mismatch between human intuition and cosmic scale, not a flaw in the idea itself. The repeating universe also reframes the edge of reality as a statistical boundary. Beyond a certain scale, novelty does not increase. Variation gives way to redundancy. Reality becomes self-similar, not because it is simple, but because it is vast. This is not visible from within any single region. From our perspective, the universe appears unique. Only by extrapolating beyond observation does repetition emerge. This again highlights the difference between observation and inference. What exists beyond the edge of reality is not directly experienced, it is deduced. And this deduction remains tentative. Cosmology is not finished. Future theories may alter this picture. Space may be finite. Laws may vary. Infinity may be replaced by something more subtle. But the repeating universe idea serves as a powerful reminder. Reality, when extended beyond human scale, behaves in ways that challenge narrative thinking. It suggests that the universe is not a story written once, but a pattern woven endlessly. If this is true, then beyond our observable reality lies not mystery in the sense of the unknown, but mystery in the sense of excess. Too much existence for any single perspective to contain. The edge of reality, in this context, is the point where uniqueness gives way to inevitability. As we continue, the next question deepens further. If space can repeat, could reality itself branch into parallel versions with different laws? Not just repetition of the same, but coexistence of the different. This leads us directly into the concept of the multiverse. and the possibility that reality is not one, but many. The idea of the multiverse represents one of the most radical extensions of modern cosmology. It goes beyond the claim that the universe is large or infinite. It suggests that reality itself may be plural. Not one universe with distant regions, but many universes existing simultaneously, each with its own properties, laws, and histories. To understand why physicists take this idea seriously, it is important to clarify what is meant by multiverse. It is not a single theory. It is a category of consequences that emerge from several independent lines of research. Inflation, quantum mechanics, and fundamental physics all point, in different ways, toward the possibility that reality contains more than one universe. One route to the multiverse comes directly from inflation. As discussed earlier, eternal inflation suggests that space continues expanding in some regions while inflation ends in others. Each region where inflation ends becomes a universe like ours. These universes are embedded in a larger inflating background and are causally disconnected from one another. In this picture, universes are not separated by ordinary space. They are separated by cosmic history. Each universe forms when inflation locally stops, cooling and allowing particles, forces, and structures to emerge. Beyond its boundary lies inflating space that prevents any interaction. These universes are sometimes called bubble universes. They are not created in a single moment. They form continuously as inflation proceeds. Reality becomes a constantly branching structure, producing universes the way stars produce light. Another route to the multiverse arises from quantum mechanics. At the smallest scales, physical systems do not have single outcomes. They exist in superpositions of possibilities. When measured, one outcome is observed, but the theory itself does not specify why that outcome occurs rather than another. One interpretation of this process suggests that all possible outcomes occur, but in separate branches of reality. Instead of probabilities collapsing into a single result, the universe splits into multiple versions, each realizing a different outcome. This idea is known as the many worlds interpretation. It does not require new equations. It takes the mathematics of quantum mechanics at face value. The price is ontological. Reality becomes enormously larger than what we experience. In this framework, the edge of reality is not spatial, it is quantum. Every interaction that has multiple possible outcomes leads to branching. Reality becomes a constantly diverging tree of histories. These branches do not interact. Once separated, they evolve independently. Each branch contains observers who perceive a single, consistent history. From within any branch, reality appears singular and complete. This is crucial. The multiverse does not feel like a multiverse from the inside. It feels like one world. A third route to the multiverse comes from attempts to unify fundamental forces. Theories that aim to describe physics at the deepest level often predict many possible vacuum states. Each vacuum corresponds to a different set of physical laws. In this view, the laws of physics are not unique. They are solutions within a vast space of possibilities. Different regions of reality may settle into different solutions. This is sometimes called the landscape. It suggests that reality contains an enormous number of possible universes, each defined by different constants, dimensions, and particle properties. Inflation provides a mechanism to populate this landscape. As inflation proceeds, different regions fall into different vacuum states, creating universes with different physics. This connects the multiverse to the problem of fine-tuning. The physical constants in our universe appear delicately balanced. Small changes would prevent stars, chemistry, or life. In a single universe framework, this fine-tuning demands explanation. In a multiverse framework, it becomes selection. Most universes are lifeless. A small fraction permit complexity. Observers inevitably find themselves in those regions. This does not prove the multiverse, but it shows why the idea has explanatory power. It turns a mystery into a statistical outcome. Critics argue that this is not explanation, but evasion. They argue that invoking unseen universes to explain observed parameters stretches science beyond its limits. Supporters respond that science has always inferred unseen structures when theories demand them. Atoms were once unseen, fields were once abstract, curved space-time was once unimaginable. Reality has repeatedly turned out to be larger than direct experience. The key question is not whether the multiverse feels strange, it is whether it follows logically from well-supported theories. At present, the answer remains uncertain. Some aspects of multiverse theory may be testable indirectly. Others may remain forever beyond observation. This raises a difficult issue. If something cannot be observed, even in principle, can it be considered part of science? Opinions differ. Some argue that testability is essential. Others argue that coherence, consistency, and explanatory power also matter. The multiverse sits at this boundary. It is not pure speculation, but it is not directly confirmable either. Yet, even as a hypothesis, it profoundly reshapes the concept of reality. Reality becomes not a single structure, but an ensemble, not a finished object, but a space of possibilities. This forces a re-evaluation of what it means to ask what exists. Existence may not be binary. Something may exist in some universes but not others. Laws may be local rather than universal. This challenges deeply rooted assumptions. Humans tend to think of reality as one world, one history, one set of rules. The multiverse breaks this unity. But unity may be a projection of perspective rather than a feature of existence. From within any universe, reality appears unified. From outside, it may not be. This again highlights the role of observers. Observation does not define reality, but it defines experienced reality. Each observer inhabits a tiny slice of the multiverse and experiences it as complete. The edge of reality, then, is not an outer boundary. It is the limit of a particular branch or bubble. Beyond it lie other realities, equally real but inaccessible. This inaccessibility is not due to distance or energy. It is structural. Universes in the multiverse do not share space-time. There is no path connecting them. This is why the multiverse does not violate conservation laws or causality within a universe. Each universe evolves according to its own internal rules. Yet, the idea raises unsettling questions. If many universes exist, what determines which one we inhabit is identity tied to a specific branch. Do other versions of ourselves exist elsewhere? These questions blur the line between physics and philosophy, but they are not meaningless. They reflect the implications of taking theories seriously. Some worry that the multiverse undermines the idea of scientific prediction. If everything happens somewhere, what does prediction mean? The answer is subtle. Predictions become statistical. They describe distributions of outcomes rather than single events. This shift already occurs in quantum mechanics and cosmology. The multiverse extends it. There is also a psychological resistance. Humans seek closure. The multiverse offers none. There is no final universe, no ultimate version. Reality becomes open-ended. Yet openness may be closer to truth than closure. The universe has repeatedly defied attempts to box it into simple forms. What lies beyond the edge of reality in the multiverse view is not emptiness or void, it is more reality. Different reality. Reality that does not intersect with ours, but exists alongside it. This does not diminish our universe. It contextualizes it. Our universe becomes one chapter in a much larger book. And like any chapter, it is meaningful within its own narrative, regardless of how many others exist. The multiverse does not say that nothing matters. It says that mattering is local, meaning arises within universes, not across the ensemble. This idea may feel cold, but it is also liberating. It frees reality from needing a single justification. Existence does not need to converge to one outcome to be real. The edge of reality, then, is not a wall. It is a boundary of participation. Beyond it lie universes we do not inhabit, histories we do not experience, laws we do not obey. And yet, through theory, we can glimpse their possibility. As we move forward, the next question becomes even more concrete. If multiple universes exist, could they ever interact? Could there be collisions, imprints, or traces? Or are they forever sealed off from one another? This leads us to the idea of bubble collisions and the search for evidence beyond our cosmic horizon. If the multiverse exists, the most natural next question is whether its components are completely isolated, or whether interaction between universes is possible in any form. While popular imagination often treats universes as sealed bubbles floating in nothingness, modern cosmology suggests a more subtle picture. Separation does not always mean total isolation. Under certain conditions, universes may collide, overlap, or leave traces of their encounters. This idea emerges most clearly from eternal inflation. In inflationary models, bubble universes form within a larger inflating space. Inflation ends locally, creating a bubble, while the surrounding space continues to inflate. Because inflation is ongoing, new bubbles continue to form, expanding outward at nearly the speed of light. These bubbles are not static. They grow, expand, and occupy regions of the inflating background. Given enough time, collisions between bubbles become possible, not inevitable, but allowed. A bubble collision is not like two objects colliding in ordinary space. It is a collision between regions of space-time itself. When two bubble universes meet, the interaction reshapes their internal structure. Energy is released along the collision boundary. Space-time geometry is distorted. Physical conditions inside each universe may be altered. From inside one of these universes, such a collision would not look like an external invasion. There would be no foreign objects entering from outside. Instead, the collision would appear as a large-scale disturbance imprinted into the fabric of space-time. This is a critical point. If universes collide, the evidence would not appear as something obviously alien. It would appear as anomalies in the early universe, subtle patterns in radiation, deviations from perfect uniformity. This is why cosmologists have considered the possibility that traces of bubble collisions might be detectable. The most promising place to look is the cosmic microwave background, the faint afterglow of the early universe. The cosmic microwave background is remarkably uniform, but not perfectly so. It contains tiny fluctuations in temperature and density. These fluctuations seeded the formation of galaxies and clusters. They are well explained by inflation and quantum fluctuations. However, if our universe experienced a collision with another bubble during its early history, it could leave a distinctive imprint. This imprint might appear as a circular pattern, an asymmetry, or an unusual correlation in the microwave background. Searches for such patterns have been conducted. Scientists have looked for circular temperature anomalies, unusual cold spots, and deviations from statistical isotropy. So far, no conclusive evidence has been found. This absence of evidence does not rule out bubble collisions. It may simply mean that collisions are rare, or that their signatures are subtle, or that our universe formed in a relatively quiet region of the inflating background. It may also mean that collisions occurred too early or too weakly to leave detectable traces. Inflation smooths out disturbances rapidly. A collision signature could be erased before it becomes observable. There is another possibility. Collisions may occur in ways that do not affect observable physics. If two bubbles have very different properties, the collision boundary may be unstable or quickly disappear. This uncertainty highlights an important feature of multiverse ideas. They often predict phenomena that are in principle observable, but extremely difficult to detect. The edge of reality becomes experimentally elusive, not conceptually vague. Even without direct evidence, studying bubble collisions is valuable. It forces cosmology to define what interaction between universes would even mean. It pushes theory to its limits. The notion of bubble interaction also challenges the idea that universes are completely separate. If they can collide, then they are not fully isolated. They are part of a larger structure that allows interaction under specific conditions. This larger structure is not ordinary space. It is the inflating background itself. Universes are embedded within it, like regions of a phase transition in a larger medium. This analogy matters. In condensed matter physics, phase transitions occur within a material. Different phases coexist, interact, and sometimes collide. Inflationary cosmology suggests space-time itself may behave similarly. In this view, universes are not absolute entities. They are emergent regions within a deeper framework. Their boundaries are not walls, but interfaces. This reframes the edge of reality yet again. The edge of our universe is not the edge of existence. It is the boundary of a particular phase of space-time. Beyond it lies not nothing, but a different regime with different properties. Inflating space may not allow atoms, stars, or observers, but it is still physical. It still has energy, dynamics, and structure. The idea of interaction also raises the possibility of indirect influence. Even if universes cannot exchange matter or information in the usual sense, their formation may not be independent. The inflating background sets conditions. The rate of inflation, the nature of the vacuum, and the underlying field dynamics influence how bubbles form. Universes may share statistical properties, even if they never interact directly. This suggests a kind of meta-reality, a level of description above individual universes, governing their creation and distribution from within any universe. This meta-level is invisible. This invisibility does not make it unreal. It simply makes it inaccessible to direct observation. Some theorists have speculated about more exotic forms of interaction, quantum entanglement between universes, higher dimensional connections, wormhole-like links. These ideas remain speculative. They stretch current theory and lack experimental support. But they illustrate how the question of what lies beyond reality leads naturally to deeper layers of structure. One must be careful here. Speculation without constraint easily becomes fiction. The strength of cosmology lies in its discipline. Theories are judged by consistency, mathematical coherence, and connection to observation. Bubble collision research respects this discipline. It does not claim evidence where none exists. It explores what would follow if inflationary models are correct. This distinction matters. The edge of reality is not a free space for imagination. It is a region where theory is stretched, not abandoned. There is also a philosophical implication. If universes can collide, then the concept of a universe as a self-contained totality breaks down. Universes become events rather than absolutes. This challenges language. Words like universe and reality imply totality. But in multiverse scenarios, totality shifts to a higher level. What we call a universe becomes a local structure within something larger. This mirrors historical shifts. The solar system was once thought to be the universe, then the galaxy, then the observable universe. Each time, what was thought to be total became local. The multiverse may represent the next such shift. If so, then the edge of reality is not a single boundary, but a series of horizons. Each horizon marks the limit of a framework. Beyond it lies a deeper structure that reframes what came before. Bubble collisions would be the first empirical hints of such a deeper structure. They would provide evidence that our universe is not isolated. The lack of evidence so far keeps this idea speculative. But speculation grounded in theory is how science progresses. It is also worth noting that absence of collision evidence may be meaningful. It could suggest that our universe formed in a region of inflating space with low bubble density, or that inflation ended in a way that suppresses collisions. This would still be information about the larger structure. The search for bubble collisions also illustrates a broader theme. The edge of reality is not something we will cross physically. It is something we probe indirectly through subtle patterns and constraints. This requires patience and humility. It requires accepting that some aspects of reality may remain forever inferred rather than observed. Yet inference is not weakness. It is how much of science operates. We infer the existence of dark matter, dark energy, and the interior of stars. Reality often reveals itself through effects rather than direct contact. Bubble collisions, if they occurred, would be effects of interactions beyond our universe. Even if they never occurred, the theoretical possibility reshapes how we think about cosmic isolation. Our universe may be alone in practice, but not alone in principle. This distinction is crucial. Practical isolation does not imply ontological isolation. The edge of reality, then, is not a border enforced by existence, it is a border enforced by structure. Structure determines what can interact, what can influence, what can be known. Beyond that structure lies more reality, governed by the same underlying rules but arranged differently. As we move forward, the next question becomes even more abstract. If universes can exist as separate regions, what is the role of dimensions? Could there be dimensions beyond the ones we experience, providing new directions for reality to extend? This leads directly into the idea of extra dimensions and higher dimensional space. The idea of extra dimensions does not come from imagination or philosophy. It comes from mathematics. When physicists attempt to describe reality at its deepest level, the equations often demand more dimensions than the 3 of space and 1 of time that we experience. These additional dimensions are not added for creativity. They appear because the math stops working without them. To understand why extra dimensions matter, we must first clarify what a dimension is. A dimension is a direction in which movement or change is possible in everyday life. Space has 3 such directions: left-right, forward-backward, up-down. Time adds another, allowing change from past to future. These dimensions feel complete because human experience is limited to them. Yet experience is not a reliable guide to fundamental structure. Humans once experienced the Earth as flat and stationary. Deeper understanding revealed curvature and motion hidden from perception. Extra dimensions may be similar, present everywhere, yet inaccessible. The earliest serious attempt to introduce extra dimensions into physics came from attempts to unify forces. Gravity behaves differently from other forces. It is far weaker, yet acts over vast distances. Physicists sought a framework where gravity and electromagnetism could be described together. When an extra spatial dimension was added mathematically, something remarkable happened. Gravity and electromagnetism emerged from the same structure. What appeared as separate forces in 4 dimensions became aspects of geometry in higher dimensions. This result was not poetic. It was precise. Equations simplified. Patterns emerged. The idea suggested that forces might not be fundamental. They might be shadows of higher dimensional geometry. This insight did not immediately transform physics. The extra dimension had to be hidden to match observation. It could not be large or obvious. It had to be compact, curled up so tightly that it escaped detection. This introduced a crucial idea. Dimensions do not need to be large to be real. They can be microscopic, folded into every point of space. Imagine a long cable viewed from a distance. It appears one-dimensional, a simple line. Up close, it reveals thickness and circular structure. An ant walking on the cable experiences more dimensions than a human observer far away. In this analogy, humans are distant observers of reality. We perceive only large dimensions. Smaller dimensions may exist, but remain invisible because we cannot access the scales at which they unfold. Modern theories build heavily on this idea. Attempts to unify all forces consistently almost always require extra dimensions. Not 1 or 2, but many. These dimensions provide the mathematical room needed to accommodate complex interactions. This does not mean physicists believe in extra dimensions lightly. It means the alternatives fail. Without additional dimensions, the equations become inconsistent or incomplete. This places extra dimensions in a strange position. They are not observed, yet they are implied by the most successful attempts to describe reality at its deepest level.
If extra dimensions exist, then reality is not confined to the space-time we experience. What we call the universe would be a slice of a higher dimensional structure.
Beyond our familiar reality would not be emptiness, but additional directions of existence. This reframes the question of the edge of reality dramatically. The edge may not be far away in space. It may be right here, folded into every point, hidden by scale and structure. This idea challenges intuition. Humans instinctively imagine beyond as distant. Extra dimensions suggest beyond can be adjacent, yet inaccessible. Why would these dimensions be hidden? One explanation is energy. Accessing smaller dimensions may require energies far beyond what we can achieve. Particles moving through these dimensions would manifest as extremely massive states in our 4-dimensional world. This means that extra dimensions could influence physics subtly without being directly visible. Gravity, for example, may leak into extra dimensions, weakening its apparent strength in our space. This could explain why gravity is so much weaker than other forces. If gravity spreads into higher dimensions, while other forces are confined, then our experience of gravity would be diluted. This idea has been explored seriously as a solution to long-standing puzzles. This confinement leads to another concept. Our universe may be a lower dimensional surface embedded in higher dimensional space. Matter and forces may be restricted to this surface, while gravity alone explores the full structure. In this picture, we are not inhabitants of all dimensions. We are confined to a subset. Reality extends beyond us, but we are pinned to a slice of it. This makes the edge of reality a boundary of access rather than existence. Beyond our accessible dimensions lie regions we cannot enter, not because they are far, but because the laws of physics restrict us. Such restrictions are not arbitrary. They emerge from the dynamics of fields and forces. Particles may be bound to certain dimensions due to how they interact with underlying structures. This is not unlike how electrons are bound to atoms. The rest of space exists, but electrons cannot occupy just any location. Their allowed states are constrained. Extra dimensions may be real, but inaccessible in the same way, not forbidden by logic, but by dynamics. This idea has radical implications. If higher dimensions exist, then reality is vastly richer than the visible universe. Events may occur beyond our dimensions that have indirect effects here. For example, collisions or vibrations in higher dimensions could influence the behavior of gravity. The expansion of the universe might be affected by geometry beyond space-time. Dark energy might reflect dynamics occurring in unseen dimensions. These ideas remain speculative, but they are not arbitrary. They arise from attempts to explain observed phenomena that resist simpler explanations. Extra dimensions also blur the distinction between inside and outside. If higher dimensions permeate our space, then beyond reality is not a separate region. It is an extension woven through what we already inhabit. This challenges the language of edges entirely. There is no boundary to cross, there is only depth to access. From this perspective, the universe may resemble a projection, a lower dimensional image cast by a higher dimensional structure. What we see is consistent and complete within its domain, but incomplete relative to the whole. This idea resonates with earlier themes. The observable universe is not the entire universe. Space-time may not be the entire reality. At each level, what appears fundamental may turn out to be emergent. Extra dimensions also offer a new way to think about unification. Forces that appear distinct in 4 dimensions may unify naturally in higher dimensions. Particles may be modes of vibration or geometry rather than fundamental points. This shifts the meaning of what exists. Existence becomes geometric rather than material. Reality becomes structure rather than substance. Such abstraction is uncomfortable. Humans prefer tangible entities, but physics has repeatedly shown that abstraction reveals deeper truth. Fields replaced particles. Space-time replaced absolute space and time. Extra dimensions may be the next step, yet caution is necessary. Mathematical consistency alone does not guarantee physical reality. Many mathematically consistent structures exist that do not describe our universe. The challenge is to find observable consequences, subtle deviations in gravity, missing energy signatures, effects at extremely small scales. So far, no conclusive evidence has been found. This absence does not falsify extra dimensions. It constrains their size and properties. They must be small, hidden, or structured in ways that evade detection. This again highlights a pattern. The deeper layers of reality become harder to access, not because they are unreal, but because they operate at scales or in directions removed from experience. If extra dimensions exist, then the edge of reality is not a frontier of space, it is a frontier of dimensionality. Beyond our familiar reality lies a multidimensional structure that contains it. We are not at the center of existence, we are embedded within it. This has philosophical consequences. It suggests that reality is layered, that what we perceive is a cross-section, that deeper truths may be orthogonal to experience. It also reframes questions about origin and destiny. The beginning of our universe may correspond to a transition or configuration in higher dimensions. Its end may be influenced by dynamics beyond space-time. This does not imply purpose or design. It implies structure. Structure does not require intention. It requires consistency. Extra dimensions offer a way for reality to be both finite in experience and infinite in structure. Our accessible universe may be limited, while the full reality is vast beyond comprehension. This possibility satisfies a recurring tension. The universe feels both complete and incomplete. Extra dimensions allow both to be true. Yet, until evidence appears, this remains a hypothesis, a powerful one, grounded in theory but unconfirmed. Still, its implications cannot be ignored. If reality includes more dimensions than we experience, then asking what exists beyond the edge of reality becomes misguided. Reality does not end. It extends in directions we cannot sense. The edge is not a wall, it is a limit of access. As we continue, the next step is to examine a specific framework that makes extensive use of extra dimensions and has reshaped modern theoretical physics. A framework where reality is built not from particles alone, but from extended objects existing in higher dimensional space. This leads directly into string theory and the hidden architecture of existence. String theory emerges not as a single idea, but as a response to failure. When physicists attempted to combine quantum mechanics with gravity using conventional methods, the mathematics broke down. Infinities appeared that could not be removed. Predictions became meaningless. Something fundamental was missing. String theory was proposed as a solution to this breakdown. Its central claim is deceptively simple. The fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. Everything we observe arises from different vibrational modes of these strings. This change from points to strings has profound consequences. Point particles interact at exact locations, leading to infinite quantities when gravity is involved. Strings, having length, smear interactions over space, softening infinities and restoring consistency. This alone would be significant. But string theory does more. When the equations are written down carefully, they refuse to work unless the universe has extra dimensions, not optionally, necessarily. In most versions of string theory, space-time must have 10 or 11 dimensions for the mathematics to be consistent. 4 are familiar, the others are hidden. This requirement is not imposed by aesthetic preference. It is demanded by internal logic. Without extra dimensions, the theory collapses. This places string theory in a unique position. It does not merely allow extra dimensions, it predicts them. If string theory is correct, then the reality we experience is not the full reality. It is a lower dimensional slice of a higher dimensional structure. What we perceive as particles are vibrations of strings moving through dimensions we cannot see. These extra dimensions are not vast like ordinary space. They are compact, curled up at scales far smaller than atoms. Every point in space contains them. They shape the behavior of strings and therefore determine the properties of particles. This leads to a remarkable conclusion. The properties of matter may be geometric, particle masses, charges, and interaction strengths could be determined by the shape and topology of hidden dimensions. Reality, at its deepest level, would be architecture rather than substance. This reframes the question of what exists beyond the edge of reality. Beyond space-time may lie structure that defines space-time itself. Space and time would not be fundamental. They would be emergent. String theory suggests that what we call space-time arises from deeper entities interacting in higher dimensions. Gravity, in this view, is not a force in the usual sense. It is a manifestation of geometry and vibration. This idea aligns with earlier insights from relativity, where gravity is curvature of space-time rather than a force acting within it. String theory extends this idea further. Space-time itself may be secondary. This has dramatic implications for the concept of an edge. If space-time is emergent, then asking what lies beyond space-time is like asking what lies beyond a shadow. The shadow is not the full object. It is a projection. Beyond our experienced reality would lie the underlying structure casting the projection. String theory also introduces new kinds of objects beyond strings. Membranes, higher dimensional surfaces, and extended entities appear naturally in the theory. These objects can have various dimensions existing within the higher dimensional space. This suggests that reality is populated not just by particles, but by extended structures interacting across dimensions. Some of these structures could be large relative to the hidden dimensions, shaping the universe in subtle ways. Others could be microscopic, influencing physics only at extreme energies. This complexity makes string theory difficult to test. Its predictions often occur at scales far beyond current experimental reach. This has led to criticism. A theory that cannot be tested risks drifting into metaphysics. Yet string theory continues to attract serious attention because it unifies gravity and quantum mechanics in a consistent framework. No other known theory has achieved this convincingly. String theory also connects seemingly unrelated ideas. Black holes, entropy, information, and geometry become aspects of the same underlying structure. Insights from string theory have deepened understanding even in areas not directly related to its original goals. This suggests that even if string theory is not the final description of reality, it may be pointing in the right direction. One of the most striking consequences of string theory is the sheer number of possible solutions it allows. Different shapes of hidden dimensions produce different physical laws. The number of possible configurations is enormous. This leads to the idea of a landscape of solutions. Each solution corresponds to a different universe with different physical constants and properties. This landscape connects directly to multiverse ideas. String theory does not predict a single universe. It predicts many possible universes. Inflation provides a mechanism to realize them physically. In this combined picture, reality consists of a vast landscape of possible universes, each realized somewhere through inflationary processes. Our universe is one realization among many. This is a dramatic departure from traditional physics. Instead of explaining why the universe has certain properties uniquely, physics explains why many possibilities exist. The explanation for why we observe our particular universe becomes statistical rather than deterministic. This shift is deeply unsettling to some. It challenges the idea that science should provide unique answers. Others argue that it reflects reality more honestly. String theory also reshapes the concept of what exists beyond the edge of reality by introducing the idea of duality. In some cases, two very different-looking theories describe the same physics. A universe with gravity in one description can be equivalent to a universe without gravity in another description. A higher dimensional theory can be equivalent to a lower dimensional one. This suggests that dimensionality itself may not be fundamental. Reality may admit multiple equivalent descriptions, none of which is privileged. This undermines the idea of an absolute edge. If reality can be described in different ways, then boundaries depend on description, not existence. One particularly striking example is the idea that information about a volume of space can be encoded on its boundary. This implies that the interior is not independent of the surface. Reality behaves like a projection. In such a framework, asking what lies beyond the edge becomes ambiguous. The edge may contain all the information needed to describe what appears beyond it. This does not mean beyond does not exist. It means that existence may be relational rather than absolute. String theory therefore challenges the basic categories humans use: inside and outside, fundamental and emergent, simple and complex. It suggests that reality is layered, interconnected, and context-dependent. Yet string theory remains incomplete. It lacks a single definitive formulation. Many versions exist, many questions remain unanswered. This incompleteness mirrors the theme of this documentary. Reality itself may not be neatly packaged. Understanding may always be provisional. String theory also highlights the limits of human intuition. The mathematics is abstract, high-dimensional, and far removed from sensory experience. Understanding it requires abandoning everyday concepts. This makes communication difficult. Metaphors break down. Language strains. Yet, this difficulty does not imply meaninglessness. It implies depth. String theory proposes that the universe we experience is a surface phenomenon. Beneath it lies a richer structure that generates it. If this is correct, then beyond the edge of reality lies not emptiness, but foundation. The edge would not be a boundary between something and nothing. It would be a boundary between description levels. We would be inhabitants of an emergent layer, perceiving reality as fundamental when it is not. This realization is humbling. It suggests that even our most basic intuitions may be contingent. It also offers a strange comfort. If reality is deeper than it appears, then mystery is not a failure of understanding, it is an invitation. String theory does not claim to have reached the bottom. It claims that the bottom may be deeper than we thought. This aligns with the recurring pattern of science. Each time we think we have reached the foundation, a deeper layer emerges. The edge of reality recedes. As we move forward, the next step is to examine an even more concrete idea that arises from higher dimensional theories. The idea that our universe may be a surface within a higher dimensional space. Not metaphorically, but physically. This leads directly into the concept of brains and the possibility that reality itself is layered like a stack of worlds. The concept of brains takes the idea of extra dimensions and gives it physical structure. Instead of imagining dimensions as abstract directions alone, brain theory suggests that reality itself may be layered. Entire universes could exist as surfaces embedded within higher dimensional space, coexisting without direct awareness of one another. A brain is a multidimensional object. Its dimensionality can vary. Some brains may be one-dimensional, like strings. Others may be two-dimensional surfaces or higher dimensional volumes. Our universe, according to some models, could be a three-dimensional brain embedded in a higher dimensional space. In this picture, everything we observe, matter, light, forces except gravity, is confined to the brain. Particles are bound to it. Interactions occur within it. From our perspective, this confinement is invisible. It simply appears as the natural structure of reality. Gravity behaves differently. It is not confined in the same way. It can propagate into the higher dimensional space beyond the brain. This provides a potential explanation for one of the deepest puzzles in physics: why gravity is so weak compared to other forces. If gravity spreads into extra dimensions while other forces remain trapped on the brain, then its apparent weakness is an illusion. It is not intrinsically weak. It is diluted across a larger space. This idea has been explored seriously because it connects abstract theory to observable phenomena. Deviations in gravitational behavior at small scales could reveal the presence of extra dimensions and brains. So far, experiments have not detected such deviations, but the constraints help refine models. Brains must be arranged in ways that hide their effects at accessible energies. Brains also introduce a new way to think about what exists beyond the edge of reality. Beyond our universe may lie other brains. Entire worlds existing parallel to ours, separated not by distance in space, but by position in higher dimensions. These parallel brains could be extremely close in a higher dimensional sense, yet completely invisible to us. No light can cross the separation. No particles can travel between brains. The separation is not spatial in the ordinary sense. This creates a striking possibility. Reality may be crowded with worlds, stacked like pages in a book, each unaware of the others. This idea differs from the multiverse of inflation. Here, universes are not separated by cosmic expansion. They coexist within the same higher dimensional structure. Their separation is geometric, not temporal. Interaction between brains is usually suppressed, but not necessarily impossible. Under certain conditions, brains could influence one another through gravity or other subtle effects. Some models suggest that collisions between brains could occur. Such a collision would be catastrophic. It could release enormous energy and radically reshape space-time. One speculative idea proposes that the Big Bang itself was the result of a brain collision. Two higher dimensional surfaces collided, injecting energy into our brain and triggering expansion. This idea is not widely accepted, but it illustrates how brain theory reframes cosmic origins. The beginning of our universe may not be an absolute beginning. It may be an event within a larger structure. If so, then what exists beyond the edge of reality includes not only other universes, but the space in which universes reside, a higher dimensional arena where brains move, interact, and evolve. This arena is sometimes called the bulk. The bulk is not empty. It contains geometry, energy, and possibly fields that govern the behavior of brains. From our perspective, the bulk is completely hidden. We cannot see it. We cannot travel into it. Yet it may determine fundamental properties of our universe. This again shifts the meaning of beyond. beyond reality is not outside existence, it is outside accessibility. Brain models also allow for asymmetric realities. One brain may have different physical laws from another. Particle content, force strengths, and dimensionality could vary. This makes reality highly plural, not just many universes, but many kinds of universes. Yet, these universes would not be arranged in a simple hierarchy. None is more real than another. Each is complete within its own domain. This undermines the notion of a privileged universe. Our reality would not be central or fundamental. It would be one layer among many. This idea resonates with earlier shifts in human understanding. Earth was not the center of the solar system. The solar system was not the center of the galaxy. The galaxy was not the center of the universe. Brain theory suggests the universe itself may not be central. This is a recurring theme. Each expansion of understanding displaces human centrality. Brains also complicate the idea of dimensionality. Dimensions may not be uniform across reality. Some may be accessible in one universe and inaccessible in another. This raises questions about what it means to exist in a dimension. Dimensional access becomes a property of a universe, not a universal feature. It also raises questions about causality. Events on one brain may influence another indirectly through the bulk. Such influence would be subtle and difficult to detect, but not forbidden by theory. This opens the door to speculative ideas about hidden influences. Unexplained phenomena in our universe could, in principle, be effects of structures beyond our brain. Most physicists approach such ideas with caution. Extraordinary claims require extraordinary evidence. Brain theory provides a framework, not confirmation. Yet the framework itself is valuable. It expands the conceptual space of cosmology. It shows how reality could be structured in ways far beyond everyday intuition. Brains also force a reconsideration of boundaries. The edge of our universe would not be a place where space ends. It would be a boundary of confinement. Beyond that boundary, space continues. But we are not part of it. This is similar to how fish experience water. The water does not end at the surface. The fish's world ends there. From this perspective, humans may inhabit a cosmic aquarium. Beyond our perceived reality lies a larger environment we cannot enter. This analogy is imperfect, but it captures the asymmetry. The larger structure exists regardless of our awareness. Brain theory also suggests that reality is stratified. There may be multiple levels of description, each valid within its domain. What we call fundamental may be emergent from a deeper layer. What we call beyond may be closer than we think. This again undermines the idea of a final edge. Reality may not terminate, it may simply change character. The edge of reality becomes a change in rules rather than a cessation of existence. This view is consistent with much of modern physics. Laws change with scale. Phases change with conditions. Boundaries mark transitions, not endings. Brains provide a way to formalize this idea cosmologically. They also reintroduce an ancient intuition in a new form. The idea of layered worlds has appeared in mythology and philosophy across cultures. Brain theory strips away myth and replaces it with mathematics. This does not validate myth. It shows that human intuition sometimes anticipates structure, even when details are wrong. The challenge now is evidence. How could brains be detected? Possible signals include deviations in gravity at small distances, missing energy in particle collisions, or cosmological signatures imprinted in the early universe. So far, none have been observed conclusively. But absence of evidence is not evidence of absence. Brain theory remains a candidate framework, not a confirmed description. Yet its implications are profound. If brains exist, then what lies beyond the edge of reality is not abstract speculation, it is physical structure beyond our confinement. We would be inhabitants of a surface, unaware of the space in which it floats. This realization reshapes humility. We are not just small in size. We may be small in dimensional access. The universe we experience may be only a slice of what exists, and beyond that slice lies a reality we can infer but not enter. As this exploration continues, the next step is to confront an even deeper question. If our universe may be embedded within something larger, could the entire universe itself be contained within something else? Not just dimensions beyond, but a hierarchy of containment. This leads us to ask whether our universe could exist inside a larger structure entirely, and what that would mean for the idea of reality. The idea that our universe could exist inside something larger pushes cosmology to its conceptual limits. It asks not merely what lies beyond the observable universe, or beyond space-time, but whether the entire cosmos we inhabit is itself a contained structure, not metaphorically, but physically. If true, this would mean that what we call reality is a subsystem of a deeper reality. This idea initially feels absurd because humans instinctively treat the universe as the ultimate container. By definition, the universe is everything. To suggest that it exists inside something else appears to misuse language, yet history shows that such intuition has failed before. The Earth was once everything, then the sky, then the galaxy. Each time, what was thought to be total turned out to be local. Physics does not forbid containment. It forbids only certain kinds of containment. Space cannot be embedded inside space in the same way objects are embedded within rooms. But space-time could be embedded in a higher dimensional structure. Geometry allows this. From this perspective, our universe would not be floating inside another universe like an object in a box. It would be a region, a configuration, or a phase within a larger framework. Containment would be structural, not spatial in the everyday sense. One way to think about this is through analogy. Consider a whirlpool in a river. The whirlpool has structure, boundaries, and internal dynamics. It can be studied as a distinct system. Yet it exists entirely within the river. It is not separate from the river. It is a pattern within it. Our universe could be similar. A stable pattern within a larger reality. Space-time, particles, and forces would be features of that pattern, not the whole. This idea appears in several theoretical contexts. In some models of quantum gravity, space-time emerges from more fundamental degrees of freedom. These degrees of freedom do not live in space-time. Space-time is something they generate collectively. If this is correct, then the universe is not fundamental. It is emergent. What exists beyond it is not another place. It is the substrate from which it arises. This substrate may not resemble anything familiar. It may not have space, time, or matter as we understand them. It may be informational, mathematical, or relational in nature. This challenges the idea of an edge entirely. If space-time itself is emergent, then there is no meaningful sense in which space-time has an outside. Asking what is outside space-time is like asking what is outside a pattern. The pattern exists within something else, but that something else is not a place. This view aligns with developments in quantum information theory, where space-time geometry appears linked to patterns of entanglement. Distances, connectivity, and even dimensionality may arise from how information is correlated. In such models, the universe is not a container of information, it is an expression of information. This reframes the question of existence. What exists fundamentally may not be objects, but relationships, not things, but connections. If reality is relational at its core, then containment becomes a matter of structure rather than location. The universe could be one relational structure among many. Another approach to this idea comes from black hole physics. Studies suggest that information about what falls into a black hole is not lost, but encoded in subtle correlations on its boundary. This implies that a lower dimensional surface can encode a higher dimensional volume. This raises a striking possibility. Our universe itself could be encoded on a boundary of a higher dimensional structure. What we experience as volume may be a projection of something more fundamental. In this view, the universe is not inside something else in the ordinary sense. It is derived from something else. This possibility undermines the notion of a final layer. If space-time emerges from something deeper, then that deeper layer may itself emerge from something else. Reality becomes hierarchical. This hierarchy does not necessarily extend infinitely. It may terminate at a fundamental level, but from our perspective, there may be several layers between experience and foundation. Each layer would have its own effective laws, concepts, and limitations. What seems fundamental at one level becomes emergent at the next. This pattern is familiar in science. Temperature emerges from particle motion. Solidity emerges from electromagnetic interactions. Life emerges from chemistry. None of these are illusions. They are real at their level. Space-time itself may be similar. Real, but not fundamental. If this is true, then the edge of reality is not something we approach by traveling farther. It is something we approach by probing deeper, by understanding how familiar structures arise. This has implications for cosmology. The beginning of the universe may not be the beginning of existence. It may be a transition, a reconfiguration, a phase change within a deeper system. The Big Bang, in this view, is not a creation event. It is a boundary in description. Our equations break down there not because nothing existed, but because space-time itself ceased to be a useful concept. What existed before the Big Bang may not be describable in spatial or temporal terms, not because it is mystical, but because those concepts did not apply. This again challenges human intuition. We think in time and space because we live within them. Imagining existence without them is difficult. Yet difficulty does not imply impossibility. Mathematics routinely describes structures that defy visualization. If the universe exists inside something larger, then our sense of totality is an illusion born of perspective. We experience all that we can interact with and mistake that for all that exists. This has philosophical consequences. It suggests that ultimate reality may be permanently beyond full comprehension, not because of technological limits, but because our cognitive tools are adapted to emergent layers, not foundations. Yet, this does not render inquiry meaningless. Understanding emergent layers has immense value. We do not need to understand quarks to build bridges. We do not need to understand quantum gravity to understand stars. Knowledge is layered, like reality itself. The idea of containment also reshapes existential questions. Meaning does not require fundamentality. A novel written on paper is meaningful, even though the paper is not the story. Our universe can be meaningful, even if it is not ultimate. This counters a common fear that if reality is larger than our universe, then our existence is diminished. In fact, it is contextualized, not negated. A painting is not less meaningful because it hangs in a gallery rather than floating in void. If anything, being part of a larger structure can enrich understanding. It connects local experience to a broader framework. However, this view also demands humility. It suggests that even the universe itself may not be the final word, that our most basic assumptions may one day be reframed. This humility has always accompanied scientific progress. Certainty shrinks as understanding deepens. The idea that our universe could exist inside something else is not a claim of fact. It is a logical possibility emerging from serious attempts to understand reality at its deepest level. It is neither proven nor dismissed. It remains a frontier idea, but its implications are consistent with a recurring theme. Every time we have assumed we reached the ultimate layer, we discovered another beneath it. This suggests a pattern. Reality may not have a single edge, it may have many transitions. What we call beyond may simply be another layer of description, governed by different rules. In this light, the question, what exists beyond the edge of reality, transforms. The answer may be not another place, but another way of existing. And if that is true, then the edge of reality is not something to cross, it is something to reinterpret. As we move forward, the next step is to examine a dimension that does not fit neatly into space or containment at all time. If reality has layers and hierarchies, what does time mean within them? Could time itself be bounded? Could there be a beyond time? This leads us to one of the deepest questions in physics and philosophy. What exists beyond time itself? Time feels fundamental because we live inside it. Every thought, every memory, every observation unfolds along its flow. We cannot step outside it. We cannot stop it. We cannot move backward through it. Because of this, time feels like the deepest layer of reality. Yet modern physics increasingly suggests that time may not be fundamental at all. It may be emergent, directional only in certain contexts, and possibly absent at the deepest level of existence. To ask what exists beyond time is therefore not a poetic question, it is a serious, scientific, and philosophical one. If time has limits, then reality may extend into domains where time, as we understand it, does not apply. In classical physics, time is absolute. It flows uniformly, independently of what happens in space. This view is intuitive and closely matches human experience. Events happen in sequence. Causes precede effects. The past is fixed, the future is open. This view was shattered by relativity. Time is not universal. It depends on motion and gravity. Clocks tick at different rates depending on speed and gravitational potential. There is no single cosmic clock ticking for the entire universe. This alone suggests that time is not a simple background parameter. It is intertwined with space, forming space-time. Geometry determines how time flows. Yet even space-time may not be fundamental. Attempts to unify relativity with quantum mechanics often run into a problem. Time behaves very differently in each framework. In quantum mechanics, time is external. It is not something that fluctuates or becomes uncertain. It is a parameter against which change is measured. In general relativity, time is dynamic. It can stretch, slow, and warp. When these two frameworks are combined, the concept of time becomes unstable. Equations describing the universe at the deepest level often lack time entirely. They describe relationships between configurations, not evolution through time. This leads to a startling possibility. At the most fundamental level, the universe may not evolve in time at all. It may simply exist as a whole. Change and flow may emerge only when viewed from within certain subsystems. This idea is known as the timeless view of reality. In this view, time is not an ingredient of the universe. It is a perspective that arises when parts of the universe interact in particular ways. To understand this, consider a book. The entire story exists at once. The beginning, middle, and end coexist. Yet a reader experiences the story sequentially, page by page. The flow of time is not in the book itself, it is in the act of reading. The universe may be similar. The full structure may exist timelessly. Observers, embedded within it, experience time because of how information is processed locally. This analogy is imperfect, but it captures a key idea. Time may be emergent from correlation, memory, and causality, not fundamental existence. If this is true, then asking what exists beyond time is like asking what exists beyond the act of reading. The answer is not another moment, it is the structure that gives rise to moments. This view finds support in the study of entropy. The arrow of time, the distinction between past and future, is closely tied to entropy increase. Systems evolve from ordered to disordered states. This gives time its direction. But entropy increase depends on initial conditions. It depends on the universe starting in a highly ordered state. Physics does not require this. It simply observes it. This suggests that the arrow of time is not fundamental. It is contingent. It arises because of how the universe began, not because time itself demands it. If the universe began in a low entropy state, then time appears to flow forward. If it began differently, the arrow could be absent or reversed. This again suggests that time is not a universal feature of reality, it is a property of certain histories. This becomes especially relevant when considering the beginning of the universe. At the Big Bang, our equations suggest that time itself begins. Asking what happened before becomes problematic. Before implies time. If time began at the Big Bang, there is no before. Yet this conclusion depends on taking space-time as fundamental. If space-time is emergent, then the Big Bang may not be the beginning of existence. It may be the boundary of applicability for time. What existed before the Big Bang may not be describable as earlier. It may be orthogonal to time entirely. This leads to the idea of a timeless phase of reality, a domain where change does not occur in the familiar sense, where there is no past or future, only structure. From such a domain, time could emerge as a derived concept when certain conditions are met, when systems become sufficiently complex, when correlations form, when memory becomes possible. This idea appears in various approaches to quantum gravity. In these approaches, the fundamental description of reality involves relationships between states rather than evolution through time. Time appears only when a subset of variables is used as a reference. One part of the system plays the role of a clock relative to another. This relational view of time means that time is not a background. It is a comparison. It exists only between systems. If this is correct, then beyond time lies not chaos or nothingness, but a deeper order without temporal labels. This has implications for the fate of the universe. If time is emergent, then its end may also be emergent. Scenarios like heat death describe what happens as entropy increases and structure dissolves. Time continues to exist, but nothing interesting happens. But in a deeper sense, the end of time may occur when correlations break down, when no subsystem can function as a clock for another, when everything becomes maximally disordered. At that point, time would not end with an explosion or collapse, it would fade, not because reality ceases, but because change loses meaning. Beyond that point, reality may still exist, but not as a sequence of events. It would exist as a static or timeless structure. This challenges the idea that existence requires time. Perhaps existence simply is. Time is how certain parts of existence experience change. This idea also reframes questions about eternity. Eternity is often imagined as infinite time, endless duration. But timeless existence is not endless time, it is the absence of time altogether. This is difficult to imagine, because imagination itself unfolds in time, yet difficulty does not imply impossibility. Mathematics routinely handles timeless structures. Equations do not evolve, they simply are. Their implications can be explored, but the structure itself is static. Reality at its deepest level may be similar. Dynamic appearance may arise from static structure. This idea also affects how we think about causality. Cause and effect are time-based concepts. If time is emergent, then causality may be emergent too. At the fundamental level, relationships may not be causal, they may simply coexist in a consistent structure. Causality emerges when time emerges. This suggests that the ultimate foundation of reality may be a causal, not random, but not ordered by before and after. This again challenges intuition. Humans rely on causality to make sense of the world. Removing it feels like removing logic itself. Yet quantum mechanics already challenges classical causality. Correlations exist that cannot be explained by local cause and effect. Deeper structures may challenge it further. Asking what exists beyond time therefore leads to a profound conclusion. Beyond time may lie the foundation of reality itself, not another era, not another timeline, but a domain where temporal concepts do not apply. This does not mean that time is illusory. Illusions do not obey precise laws. Time obeys laws extremely well. It is real within its domain. It means that time may be contextual rather than absolute. This contextuality mirrors earlier themes. Space may be emergent. Laws may be local. Universes may be plural. Time may be relational. Each step removes an assumed absolute and replaces it with a structure dependent on conditions. This pattern suggests that the edge of reality is not a place or a moment. It is the limit of applicability of certain concepts. Space works here, not there. Time works here, not there. Causality works here, not there. Beyond those limits, reality does not end. Our language does. This realization is both unsettling and liberating. Unsettling because it dissolves familiar anchors. Liberating because it allows reality to be deeper than imagination. When people ask what exists beyond the edge of reality, they often expect something exotic, another universe, another dimension, another realm. What may exist instead is something more radical: existence without time, structure without sequence, order without flow. This does not mean that time is meaningless. It means that time is a feature of our layer of reality, not the foundation. Our experiences, histories, and lives are real within time. They matter within time. Timelessness does not negate them. Just as the existence of atoms does not negate the reality of mountains, the existence of timeless structure does not negate the reality of moments. The universe may be layered. Time exists in some layers, not in others. The edge of time may therefore mark a transition between layers, not an end. This brings us to a critical point. If space and time may both be emergent, then what we call reality may be built from something even more abstract. The next step is to explore one of the most provocative ideas arising from this line of thought: the possibility that reality at its deepest level is not made of matter or energy, but of information itself. If so, then beyond space and time lies not emptiness, but code, structure, and relation. This leads us directly to the idea of informational reality and the possibility that the universe is fundamentally computational in nature. The question of what existed before the beginning of the universe is one of the most persistent and misunderstood questions in cosmology. It arises naturally from human intuition. Beginnings imply causes. Events imply prior events. Time, as we experience it, always stretches backward. So when we are told the universe had a beginning, the mind immediately asks what came before. Yet, this question may be fundamentally flawed. Not because it is foolish, but because it assumes that time existed before the universe. Modern physics increasingly suggests that this assumption may be wrong. To understand why, we must first clarify what is meant by the beginning of the universe. In standard cosmology, the universe began in a hot, dense state, often referred to as the Big Bang. This is not an explosion in space. It is an expansion of space itself. Distances between points increased rapidly from an extremely compact state. As we trace this expansion backward using known laws of physics, densities and temperatures rise. Eventually, equations predict a singularity, a point where quantities become infinite and the laws of physics break down. This singularity is often called the beginning of time. But singularities are not believed to be physical objects. They are signals that a theory has been pushed beyond its domain of validity. When equations yield infinities, it usually means something deeper is missing. The Big Bang singularity is likely not a literal beginning of existence. It is the boundary beyond which our current theories cannot reliably describe reality. This distinction is crucial. The beginning of the universe in our models may mark the beginning of space-time as we know it, not the beginning of everything. If time itself emerged at the Big Bang, then asking what happened before is like asking what is north of the North Pole. The concept ceases to apply. This does not mean nothing existed. It means existed before may not be a meaningful phrase. Yet many physicists believe that something did exist prior to the Big Bang, in a sense that does not rely on time as we understand it. Several serious proposals explore this idea. One possibility is that the universe did not begin, but transitioned. Our expanding universe may have emerged from a prior phase of reality, not earlier in time, but differently structured. In some models, the universe undergoes cycles. Expansion follows contraction. Big bangs follow big crunches. The universe rebounds rather than begins. In such models, the Big Bang is not the first event. It is a bounce, a transition from a contracting phase to an expanding one. Time may extend through this transition, but its direction may change. Entropy may reset or behave differently across cycles. These models face challenges. Entropy tends to increase, making exact cycles difficult yet modified versions remain under study. Another possibility is that the universe emerged from a quantum state at extremely small scales. Quantum effects dominate. Space-time may fluctuate wildly, losing its classical meaning. In this view, before the Big Bang there was no smooth space-time. There was a quantum regime where geometry itself was uncertain. The universe did not emerge from nothing. It emerged from a quantum structure. This structure would not be located in time. Time would arise only after the universe expanded and cooled enough for classical space-time to form. In such models, the beginning of time is not a creation event. It is a phase change. This is similar to how temperature emerges when many particles interact. Temperature does not exist for a single particle. It emerges statistically. Time may be similar. It emerges when enough degrees of freedom align in a particular way. Another class of ideas suggests that the universe is eternal into the past, but not in the way human intuition imagines. Instead of a single timeline extending infinitely backward, reality may consist of many branches, regions, or configurations without a global temporal ordering. In such a reality, our universe would be one branch where time flows in a particular direction. Other branches may exist without time or with different temporal structures. This again dissolves the idea of before as a universal concept. Some proposals suggest that the universe was born from a fluctuation, not a fluctuation in time, but a fluctuation in a timeless background. Quantum systems can exhibit transitions without external time parameters. Change can be relational rather than temporal. In this sense, the universe may not have been caused by something earlier. It may have emerged as a configuration within a larger structure. This challenges deeply held intuitions about causality. Humans expect every event to have a prior cause, but causality itself may be emergent. At the deepest level, reality may not operate by cause and effect. It may simply have constraints and relationships. What we perceive as causes may be patterns within those relationships. This idea feels unsettling because it removes the comfort of explanation by sequence, yet it may be closer to how reality actually works. Another possibility is that the universe is self-contained. Its existence does not require an external cause. It exists because it exists. This sounds circular, but physics already accepts similar principles. The laws of mathematics do not have causes. They are structures that exist timelessly. Physical reality may be anchored in similar structures. In this view, the universe is not caused, it is instantiated. This does not imply design or intention. It implies necessity. Certain structures exist because they are consistent. This idea aligns with approaches that treat reality as fundamentally mathematical. Physical existence becomes a manifestation of abstract consistency. If this is true, then asking what existed before the universe becomes a category error. The universe is not an event within time. It is a realization of a structure. Time exists within the universe, not the other way around. There is also a more modest possibility. The universe may have begun in time, but the question of before is simply unanswerable, not because it is forbidden, but because no information survives from earlier phases. Cosmic inflation, entropy increase, and horizon effects may have erased all traces of prior conditions. Even if something existed before, it left no imprint accessible to us. This would make the beginning of the universe an epistemic boundary. Beyond it, reality may exist, but knowledge cannot reach. This again highlights a recurring theme. The edge of reality often coincides with the edge of recoverable information. What existed before the beginning of the universe may be real, but unreconstructible. This is not unusual. Much of reality is like this. We cannot reconstruct the exact microstate of yesterday's air molecules. We accept this without existential discomfort. The early universe may be similar, just on a cosmic scale. Yet the question persists, because beginnings feel special. They feel explanatory. Humans want origins to anchor meaning. Physics does not share this need. It describes how systems behave, not why they exist in an ultimate sense. When physics encounters a boundary like the Big Bang, it does not declare creation. It declares incompleteness. This distinction is often lost in popular discussion. The Big Bang is described as the beginning of everything, when it is more accurately the beginning of our ability to describe the universe using known laws. This misinterpretation feeds confusion about what existed before. The honest answer from science is not nothing. It is unknown. But unknown does not mean unknowable. Theories continue to evolve. New frameworks may extend understanding beyond the Big Bang. Yet even if future theories describe a pre-Big Bang phase, the deeper question may remain: why that phase exists at all? This question may not have a scientific answer, not because science is weak, but because the question may not be well defined. Existence itself may not admit a why in the way human language expects. This is difficult to accept because humans seek narrative. Beginnings, causes, purposes. Reality may not operate narratively. It may operate structurally. The universe may exist because a certain structure exists. No earlier, no later, just existence. If this is the case, then what existed before the beginning of the universe is not an earlier thing. It is the underlying structure that allows universes to exist. This structure may be timeless, it may be mathematical, it may be informational, it may be something we do not yet have language for. What matters is that the beginning of the universe may not be the beginning of reality. It may be the beginning of our story. This perspective reframes the question of the edge of reality. The edge is not a moment where existence starts or stops. It is a boundary of description. Beyond that boundary lies something that does not fit our categories. This does not diminish the reality of the universe. It deepens it. It suggests that our universe is not arbitrary or isolated, but connected to a deeper framework. This connection may never be fully understood, but partial understanding is still understanding. Science does not require final answers to be meaningful. It progresses by extending boundaries. The question of what existed before the universe may remain open indefinitely, not because it is meaningless, but because it points toward the deepest layer of reality, and that layer may resist full articulation. As we move forward, the next step is to examine another aspect of reality that seems to dominate the universe yet remains invisible: dark matter and dark energy. If most of the universe is made of things we cannot see, then perhaps the edge of reality is not far away at all, but embedded within the cosmos itself, shaping everything without revealing itself directly.